Today on How It's Made. Magnets. We reveal the secret of their attraction. Cooked ham. The pig's short, shanked redemption. Silver-plated teapots. Spouting niceties. And crash test dummies. It's safe to say they're a smash. But first, magnets attract certain metals and each other. That's handy for more than sticking stuff to the fridge. They help run motors and generators, among other things. Magnets occur in nature, but 2 centuries ago, people figured out how to make them using electricity. You could say it was a take-charge situation. You can't see or feel the force causing this globe to levitate, but it's not magic, it's magnetic. To make magnets, they must first create a sand mold of the magnet shapes. They load this pattern of 4 magnet shapes into a machine that fills it with sand. They remove the pattern and smooth the surface, dimpled by the machine's lid. Then it's back inside, but this time the machine pumps in gases to chemically harden the sand. It takes just seconds to solidify. They lift out the sand slab, revealing the impression of the magnet pattern. It's now a mold. Magnets come in many shapes and sizes, as do their molds. Now they're ready to mold the magnet shapes. They take copper, cobalt, sulfur, nickel, pure iron, aluminium and titanium. They load all these metals into an electrical induction furnace. It generates a pulsating electromagnetic field that heats to more than 1,600 degrees Celsius, melting everything into a molten soup. They pour this into the sand molds. The molds burst into flames because the gases that harden the sand are highly flammable. They slide the blazing molds to another part of the foundry and knock them to the floor. Then they bust them open with a sledgehammer to get air inside so they cool down and the gases burn off. They shovel everything into a bin and sort the metal shapes from the sand chunks using what else? A magnet. The molded pieces react like ordinary metal. They don't yet have magnetic power. Some are shaped like rings. Threaded onto a copper pipe, they'll be used in electric motors. They place the ring-covered pipe in a much larger tube. Then they center it by packing silica sand tightly around it. The sand will hold the rings in position during the next step. They seal both ends with concrete, allowing the inner copper tube to protrude slightly. Then it's into a different electrical furnace. It heats the tube full of magnet shapes until it's red hot. This primes them to accept an electromagnetic field which will be delivered by this metal rod. They slide it down the center of the copper pipe and clamp it in place. Water keeps the pipe from melting as they deliver a low-voltage, high-current charge in a cylindrical formation, important for motor magnets. They break open the seal. The process has left the ring shapes mildly magnetized, but most importantly, it's orientated the magnetic field properly. They grind away any rough edges. At this point, these magnets are pretty useless. But this machine will empower them. It delivers an electromagnetic charge to the metal, which magnetizes it. The establishment of that weak magnetic field earlier has laid the groundwork for this moment, ensuring that the magnetization is properly orientated. Now that's some serious magnetic muscle. In their various forms, magnets continue to exert a lot of pull in our society because their invisible power helps keep so many things running. Ham is the hind leg of a pig. You can buy it raw and roast it yourself. Or you can buy it already cured and smoked. You can buy your hams boneless or with the bones still intact. Ham on the bone has more flavour because processing doesn't disturb the natural muscle, fat and bones. Thousands of hams arrive at the factory fresh from the slaughterhouse. The factory's automated sorting system weighs each ham, then knocks it into the designated vat. By grouping hams of similar size together, the factory can better control the quality of the curing and cooking process. Each vat empties into a tumbler. The machine spins the hams for about 5 minutes, loosening the skin from the meat. Tumbling makes this next step easier. Using specialized trimming tools, workers cut off the skin. They use an automatic trimming machine to skin the back portion, called the butt. In keeping with traditional style, the machine leaves just a small amount of skin on the thin part of the leg, called the shank. Now the circular wizard knife does its magic. They run it across the butt to remove all but a centimetre of fat. Finally, they chop off the base of the almost meatless shank, called the hock. Other workers prepare the curing solution: water, sugar, salt and other ingredients that are a company secret. This recipe produces that trademark ham flavour and pink colour. Without it, the meat would come out tasting like a pork roast. Pipes feed the solution to an injection machine that's equipped with 138 needles. As the hams pass underneath, the needles inject curing solution. This ensures the cure penetrates thoroughly and evenly. All that piercing also tenderizes the meat. Next, workers load a machine called the stuffing horn. Like a cannon, it fires each ham into a heat-resistant cotton net. Workers close each one with an aluminium clip, then cut off the excess. Cooking hams on trays would flatten the underside, so workers hang them by the nets to keep them nice and round. They move the cooking racks into a food processing oven, the industrial equivalent of a traditional smokehouse. They pour hickory wood chips into the oven smoker and start her up. For the next 12 hours, the hams slow cook at temperatures ranging between 65 and 82 degrees Celsius. This tenderizes the meat and gives the smoke ample time to seep in. After cooking, workers shower the hams in cold water for 10 minutes. This rinses away drippings that have fallen from higher hams onto lower ones. Then it's onto the chill area, where over the next 36 hours the hams cool to -2 degrees Celsius. The nets come off and packaging begins. The factory sells hams whole, or using a bandsaw, slices them into halves or smaller sizes, such as single portion ham steaks. Workers position a soft plastic pad over the bone, then bag the ham in plastic. The pad prevents the bone's sharp edges from ripping the package and destroying the airtight seal. They position each bag for vacuum sealing. From there, it's all automated. A vacuum chamber descends over each bag, sucking out the air and sealing the plastic. A robotic arm transfers the vacuum-sealed ham to a conveyor belt, leading to a hot water bath. Each bag spends a mere 5 seconds in hot water, but that's enough to shrink the plastic tightly around the ham. Refrigerated, the ham stays fresh in its airtight package for 3 months. Store it in your freezer, and you can ham it up for 6 months more. Tasty. Coming up after the break, silver-plated teapots. Get luxury down to a T. And crash test dummies reveal some smashing secrets. See you after the break. Welcome back to How It's Made. Teapots. The Mayans started using them 2,600 years ago, probably for hot chocolate. Their evolution spans several hundred years, and they come in a wide range of styles. More than just vessels for brewing and drinking, aficionados consider them essential for that perfect cuppa. These silver-plated teapots come in every style imaginable, and making them requires the talent and skill of an old-world master. A century-old hand-circling machine cuts a perfect circle out of a brass sheet that's 1.5 millimeters thick. They shape that brass disc with a forming die mounted inside a press. After lubricating the press surface with vegetable oil, they position the disc on the press, then cover it with a polyurethane stopper. As the press applies 3 tons of pressure, the die moves upward, shaping the disc from underneath. The stopper provides counter pressure to keep the die from breaking through the brass that thins as it stretches. They call this preliminary shape the draft shape. They insert the draft shape into another die and repeat the forming process to produce the final shape of the teapot's base. Next, they solder on the teapot rim, which was made the same way. A craftsman then hammers the metal to remove any imperfections left by the pressings, and punches in the maker's mark. Spinning is another technique they use to shape metal teapot parts. Here, a craftsman uses a tool to shape a copper teapot mounted on a lathe. They decorate the metal using a technique called hand chasing. With a paper stencil, he applies the design in white powder. He pencil traces the pattern, then hammers in the design with a variety of tools. This intricate process requires the talented hands of an expert artisan. For the teapot spout, workers press brass plates into left and right side dies. Once again, they use 1.5 millimeter thick brass and drop a 1/4 ton press to produce the final spout shape. To assemble the spout, they brush on soldering paste. Wire the 2 halves together, then fire the spout to 370 degrees Celsius. The spout gets an acid bath to remove all the impurities the soldering process left behind. Using pumice, which is crushed volcanic rock, workers polish the teapot with 3 progressively finer grades. They give it one final buffing to ensure the surface is perfectly smooth. With diamond-tipped hand tools, engravers can etch additional features, everything from custom designs to company logos. workers now screw on the lid, wire up the teapot, and immerse it in cleaning chemicals, then in a silver plating bath. Just before shipping, workers attach hardware and perform a final cleaning. Finally, shippers wrap the teapots in acid-free cellulose that prevents the silver from tarnishing. It takes a talented team of highly skilled craftspeople to create these unique teapots, in styles ranging from Elizabethan to ultra-modern. Milk and 2 sugars, please. Crash test dummies come in all shapes and sizes. They may look human, but they're actually guinea pigs for a whole range of impact tests. How do they make dummies whose form and structure mimic the human body? Here's our version of Crash Test Dummies for Dummies. Crash test dummies are designed to take some serious hits. Car manufacturers use the crash data they provide to build safer cars, vans and trucks. A dummy's anatomy is pretty simple. There's a metal skeleton made of steel and aluminium bones. Those bones contain load cells, electronic devices that measure crash force. On the outside, the dummy's skin consists of a vinyl covering. To make the load cells, a milling machine shapes steel bars using a solid carbide end mill. Lubricant cools the intense heat and washes away the metal particles. Using a precision tool called a dial indicator, they verify the load cell's dimensions to within 5/100ths of a millimeter. They install the strain gauge, the component within the load cell that measures crash force. The hair width wires that connect the strain gauges are so delicate that soldering them requires a microscope. The vertebra in the dummy's neck also contains a load cell. The strain gauge they solder inside it measures not just lateral and vertical forces, but also twist or torsional force. Now they lay out the bones and corresponding load cells that will be connected to the dummy's rib cage. To make the rib cage, steel bands are bonded to a flexible damping material. This material was originally designed to deaden sound in nuclear submarines. In a crash test, these dummy ribs compress the same way human ribs do. A technician bolts the entire rib assembly to the spinal column and covers it with a plastic chest plate called a bib. The long bones and load cell forms are inserted into aluminium molds. Then workers bolt the mold shut and pour in liquid vinyl. The molds bake at 170 degrees Celsius for 10 to 20 minutes. When they come out, the first step is to cut away flash, the excess vinyl that oozed out of the mold during the baking process. Then a technician visually inspects the components to ensure an accurate fit. This is no ordinary vinyl. It's specially designed to resemble human flesh in consistency and density. This gives researchers realistic crash data. Now they install the bones, starting with this tibia, into their respective vinyl compartments. Zips allow the engineers to remove the components easily after performing a crash test. A technician bolts all the dummy joints in place and ensures they have a human-like range of motion. Using a neck compression tool, A technician lines up a load sensor with the neck vertebra and fastens the completed neck assembly to the dummy head. Next up is the dummy's upper body. He bolts the thorax onto the pelvis, the head and neck assembly onto the thorax, then fits a vinyl jacket over the chest. He finally bolts on the limbs, containing all of those long bones and load sensors. Crash test dummies range in size from newborns all the way up to 102 kilogram adults. This enables researchers to be sure that seatbelts and airbags protect everyone equally well. It took a whole 12 weeks to make this dummy. And now, he's ready for a life of hard knocks to make travelling safer for all of us. Thank you very much. So, if you can't attract and need a little extra pulling power, or you need to ham it up in the kitchen, or perhaps you fancy a posh brew at break, now you know how it's made. Today on How It's Made. Curling stones. Putting production on ice. Refrigerators. We bring you the chilling details. Aluminium baseball bats. At this factory, production is in full swing. And opalescent glass. A gem of a story. But first, you could say curling is a combination of shuffleboard, billiards and bowling on ice. The playing pieces are large stones. The player aims a large stone at a target, while trying to knock the opponent's stones away from the target. Team members sweep brooms in the stone's path to control the speed and manipulate the trajectory. Curling stones are made of granite. But only 2 quarries in the world, in Wales and Scotland, produce the unique type for making them. It's a granite with a fine grain that contains no quartz. This special quartz-free granite has 3 times the impact resistance of regular granite. At the quarry, they try to avoid blasting, because that fractures the stone. Instead, they locate flaws in the rock face and pry chunks off it with an excavator. This one weighs about 20 tons and is the size of a small car. The next step is to divide it into more manageable slabs. The cutter is a thick cable with abrasive rings made from diamond particles. As it travels around large pulleys at high speed against the rock, the diamonds wear through the granite. Avoiding flaws and weak points, they trace circles the size of curling stones on the best quality areas. The cut slab then moves inside the quarry building. This core drill's diamond cutters bore right through the slab, excising a blank that will become a curling stone. The blanks weigh about 26 kilograms apiece. Workers lift them out with an industrial-strength suction cup, transferring them to a container bound for the curling stone factory in Canada. There, a drill bores a channel 16 millimeters wide right through the center. This is for attaching the curling stone's handle. But that's still a long way off. First, this machine has to carve the blank into the shape of a curling stone. The machine's curved arm is lined with diamond cutters. It forms half the stone. Then workers flip the blank over so it can form the other half. The next machine carves out a pocket in the bottom. This will hold an insert made of a special type of granite from Scotland that has an extra fine grain. This high-resistance insert will extend the curling stone's life. After lining the pocket with epoxy, they position the insert. A hydraulic press pushes it in, expelling any trapped air and holding it until it firmly bonds. Next, a grinding machine, following a template, makes a center cup in both the top and the bottom of the stone. Curlers can attach the handle to either cup, according to which surface of the stone they want gliding on the ice. Now workers bolt the stone to a spinning polisher. They buff the surface with 5 progressively finer grades of diamond abrasive pads. Now they blast the side with tiny glass beads. This pits the surface to better distribute impact force, preventing the side from chipping as it strikes other stones. Running the top and bottom over coarse sandpaper gives the stone more traction on ice. The finished curling stone weighs in at about 18 kilograms. The factory molds the stone's handle from durable, impact-resistant plastic. This computer-guided engraving machine can carve any name or logo onto it. It's just a matter of applying paint to the recessed areas to make the lettering or design stand out. Finally, they bolt in the finished handle through the center hole that they drilled earlier. From the quarry, to the factory, to the ice, this beautifully crafted curling stone is on its way to becoming a smashing success. Before refrigeration, people used the environment to store and preserve food. They built cellars because it was cooler underground. In cold climates, they filled shacks with snow and ice, making what were essentially ice boxes. Finally, in the 1900s, a French inventor developed the first machine to cool and preserve foods at home. The modern refrigerator comes in countless styles, sizes, and colours. Manufacturing begins with coiled sheets of steel. Just one of these coils produces hundreds of fridge exteriors. The interiors are made from rust-resistant aluminium, lined with an acrylic shell. A shearing machine slices the steel into pieces for the exterior top, back, and sides. Then each one goes into a computerized punch press to receive holes for running various wires. A brake press forces the piece against a forming die, bending the steel at the edges and corners so it will fit snugly into position. To assemble the fridge's outer shell, workers place the pieces in an assembly jig, which holds them firmly together. Now for the fridge's interior. A vacuum forming machine heats a sheet of plastic and shapes it against an aluminium mold. Then a router carves off all the excess plastic. The freezer half of the refrigerator slides perfectly into the metal outer shell, and the fridge side follows. Copper tubes filled with heated gas are laid along the outer edge, where the door contacts the fridge. The gas prevents moisture buildup. They add the pre-cut face frame of the fridge. Then they inject foam into the cavity between the interior and exterior shells. This foam not only insulates the refrigerator, but gives it structural rigidity as well. This evaporator plays a key role in keeping things cool. It draws the heat out of the fridge. The electrical hub of the fridge freezer is the control panel. It connects to a maze of wires and eventually to a microprocessor. With the freezer side almost complete, they install the evaporator for the fridge side. Next come the fridge doors. Two compressors pump fluid and gas through the various tubes inside. This component, called the radiator, dissipates the heat collected from the food. They attach the expansion valves. These allow the pressurized liquid coolant to expand into a cold gas that runs through the tubes in the fridge, absorbing its heat. They solder copper tubes to the compressor. They'll later fill these tubes with refrigerant. Temporary quick connect valves allow the system to be charged with inert gas to check for any leaks. They connect the temporary valves to hoses and add the inert gas to the sealed system. They use this wand to check the tubes for leaks. If there is a leak, the gauge goes out of the specified range. The process of refrigeration occurs as the cold gas in the evaporator coils pulls heat energy from inside the fridge. The compressor then changes the gas back to a liquid while the radiator dissipates the collected heat. That liquid then passes through the expansion valve, turns back into a cold gas and circulates again through the evaporator coils. With a charging gun, they inject refrigerant gas into each tube, then weld the ends of the tubes shut. Now for the finishing touches, starting with the refrigerator handles. Drawers for fruits and vegetables slide right in. So do the rest of the pre-made shelves and compartments. Finally, they press an adhesive logo onto the top corner of the door. Built-in, standalone, double door or traditional, the refrigerator keeps our food just the way we like it. That's cool. Coming up after the break, a hard-hitting examination of aluminium baseball bats. And looking into the world of opalescent glass. Join us after the break. Welcome back to How It's Made. The ping of aluminium bat echoes across baseball diamonds, rivaling the crack of the wooden bat. The pros still use traditional wood, but outside the major leagues, the metal bat is a definite hit. Using it means it's a whole new ballgame. Lightweight and durable, the metal bat has some definite points in its favour. They start with aircraft-grade aluminium rods. These rods are sliced into short chunks called blanks. They load the blanks one at a time into a lathe with a computerized drill. The drill tunnels through the center of the blank as it spins. Then the blank undergoes impact extrusion. With the force of a 300-ton weight, a shaping tool slams into the hole in the blank, stretching it to more than twice its length, and giving it the basic taper of a baseball bat. Stretch blanks now tumble into a big perforated drum. They lower the drum into a tank full of soapy water. As it turns, water flows through its holes, washing away any oily residue on the blanks. And now, for a serious heavy hitter. This forming tool delivers a 400-ton punch, through the centre of the back blank. The aluminium stretches around the tool to the full length and shape of a baseball bat. A technician measures the bat to confirm that it's completely straight. If it's not, she applies a little hydraulic pressure to bend it into shape. Measuring and realigning the bat is critical, because even if it's slightly crooked, it could throw the player off their game. The bat then goes into another computerized lathe. As it spins, a blade lops off the end of it to cut the bat to size. Another tool threads the inside for attaching the end cap. They lock the bat in a holding device and, using a circular saw, trim the handle end. Now that the bat has been correctly sized, it's time for a vigorous sanding. This gets rid of any small defects and roughs up the surface so paint will stick to it. They use heavy-duty paint, because baseball bats have to stand up to a lot of abuse. They load the sanded bat into a silkscreen machine and apply the trademark information. Then it's over to the decal department. They dip the decals in a solution that activates the glue and then stick them onto the taper of the bat. These decals contain additional product information. Then it's back under the paint gun for a clear coating of polyurethane. They press fit the plastic end cap to the hollow barrel. They slide an aluminium knob onto the handle end and place the assembly in an automated welding machine that fuses them together. Now for the gripping part. They wrap synthetic leather to provide a non-slip surface around the handle. They finish the edge with a little vinyl tape. From a small solid chunk of aluminium to a hollow metal baseball bat, it's been quite a journey. And now these bats are ready to show us what they're made of. Strike! Glassmaking dates back more than 40 centuries. In the late 1800s, glassmakers created something spectacular. Glass that was both milky and translucent. They called it opalescent glass. Like its namesake, the opal gemstone, its beauty lies in the way it magically catches the light. Opalescent glass is a semi-transparent glass accented with a solid colour, or a swirling mix of colours. Glassmakers create it by melting minerals such as silica sand, soda ash, dolomite, limestone, and fluorspar. Adding recycled glass helps speed up the melting process and stretches costly raw materials further. They colour the mix with pigments, in this case, cobalt oxide, which gives a distinctive blue tint. A hoist then lifts the raw ingredients, called batch, up to the mixer, which has 2 chambers. Ingredients flow from end to end between them, thoroughly blending the batch. The blended batch now goes via a wagon to the beehive, a furnace that contains 12 ceramic pots. The furnace man shovels the batch into a pot to melt at a searing 1426 degrees Celsius. He pushes any spills back into the pot. Then, to control the temperature inside, closes up the pot's mouth. "24 hours later, workers gather the glowing molten glass. With only seconds to spare, they hurry to the mixing table, keeping the glass in motion to prevent it from cooling unevenly along the way. It's critical they cool off the ladles between each use, or the next gather of glass will stick to the ladle surface. The ladles they use vary in size, holding between 2 and 18 kilograms of molten glass. Workers pour as many as 5 different ladles at once to make a single colour. The mixing table is where the magic happens. The tableman picks up one gather of burning molten glass, then another, then skillfully blends them together using a steel fork. He then flips the molten glass into a rolling machine, evening it out as it squeezes through the rollers. Out comes a sheet about 2 meters long and 3 millimeters thick. Every 90 seconds, workers fill their ladles with molten glass at 1200 degrees Celsius. Mixing the molten glass on the table helps cool it and blend the colours. This temporarily alters its appearance, but not its final colour. The tableman separates the glass sheet from the table surface, forcing out any trapped air bubbles and further cooling the glass. The sheet now goes into a leer, an oven that anneals the glass, cooling it evenly to prevent it from cracking. From there, it's onto the trimming table. Workers wear protective clothing to handle the razor-sharp edges, still hot to the touch. Cutting the glass sheets is a delicate two-man job. They must work in sync to keep apace with the sheets that keep on coming. A single pot produces about 25 sheets over 24 hours. That's 300 sheets a day from just one 12-pot furnace. Using a carbide-tipped cutter, the workers score the glass, then snap apart the pieces. Standard 81 centimetre square sheets. They set aside the excess glass to remelt in a new batch. Finally, they load the sheets into crates and ship them all over the world. Just look how artists use opalescent glass to create a feast of pattern, colour and light. Like a painting, only more fragile. So, if you're someone who gets your rocks off on ice, or you can't stand the heat and need to chill out in the kitchen, or you just want to test your metal on the mound, now you know how it's made. Today on How It's Made. Levels. At this factory, they really do their level best. Hot dogs. We'll have the frank facts from the factory. Abrasive grain. A job that has to be up to scratch. And sandpaper. A process that's all about going against the grain. But first, the spirit level was invented in the 17th century to put the right slant on things. We use it to make things plumb and true. Without it, buildings would lean, floors would be crooked, and maps would have inaccurate elevation information. So, the level really has helped us straighten out our world. It's a centuries-old concept, but it still measures up. Centering the bubble in the spirit level helps ensure you've done an even job of things. They start with a length of laminated birchwood. An automated router carves several holes in it. 3 of the holes will enclose the vials with bubbles. 2 others will serve as hand grips. Once they've carved out plenty of niches, they move on to the perimeter of the wood. They cut grooves along the length of the wood to install a brass binding. But first, they unwind the binding into a forming machine. Rollers flatten it to get rid of the curl from the coiling. Other rollers then crimp the brass. The process will allow the strip to fit into those grooves on the level's wooden casing. They load pieces of the brass binding into a machine that slides them into the grooves. This gives the wood some reinforcement along the edges. At another station, a machine melts and molds plastic to make vials. Each one is slightly curved inside, so the bubble will have a place to sit. The vials wind their way through a vibratory feeder. It takes them to a gripper that rotates each one so the open end faces up. It's time for a fill-up with yellow mineral spirits, leaving just enough room for a bubble to form. A robotic arm plugs the vial with a plastic cap. Then, this sonic welder applies high-frequency sound waves to melt the cap into the vial. The vial is then transferred to an inspection station, where a tiny camera photographs the bubble and sends the picture to a computer for verification. For this production run, the bubble should be 1.2 centimeters wide. If it's on the mark, the computer allows the vial to move on. A printer head then hot stamps the center marks onto the vial. But this spirit vial isn't quite ready. The next step is to bake them for 24 hours. The heat exposes flaws and the defective vials are ejected. Then they shine a bright red light onto a vial to illuminate it as it slowly spins between rollers. A camera photographs the bubble and a computer scans the image to check for shifting. Too much shifting could compromise the level's accuracy. The vials that pass the test then go into a molding system. It injects melted plastic into crevices to make a cradle for each vial. Next, a technician glues the cradled vials into the openings in the wooden framework, 2 to a slot. This is precision work. Each vial has to sit perfectly level. She checks her progress as it's magnified onto a monitor. Some vials are installed vertically to gauge if the verticals are plumb, while the horizontal ones let you know if the horizons are level. They fit acrylic-rimmed windows over the vials to protect them. They screw rubber caps onto both ends of the level and give it their trademark stamp. Now these levels are ready to fight crooked construction and keep the business straight. dogs are sausages in a roll. It's likely that German sausage makers came up with the idea. German immigrants were selling them from pushcarts in New York's Bowery as far back as the 1860s. A century and a half later, hot dogs are still big on the street. To make standard hot dogs, they use a mix of pork, beef and chicken. The cuts they use are called trimmings, pieces of meat left over from cutting steaks or pork chops, and they're mainly muscle tissue. They grind the trimmings the same way butchers grind hamburger meat, by pushing the cuts through a metal plate pierced with holes. They add processed chicken trimmings to the ground meat, then mix in food starch, salt, and other flavorings. The starch thickens the mix while the flavorings vary depending on where the hot dogs are to be sold, because people in different regions have different tastes. They spray water into the mix and blend everything together in a big rectangular vat. A dash of clear corn syrup adds sweetness. They mix in more water, which helps disperse the ingredients and make the hot dogs juicier. Another machine then shreds the meat batter into a fine emulsion and vacuums out any air. They load rolls of cellulose tubing into the stuffing machine. It pumps the meat puree into a long casing, twisting it every 13 centimeters, the length of one hot dog. It takes just 35 seconds to make a chain of hot dogs that would span a football pitch twice. Then, they link 3 of those hot dog chains for an even longer string and load several at a time into another machine, which drapes the hot dogs onto moving racks. It's all carefully timed so that a twist always lands on the bar. The racks shunt the hot dogs through a liquid smoke shower, then through an oven with several cooking zones. The liquid smoke seeps through the casing and adds flavour to the dogs as they bake. Hot out of the oven, they drench these franks in very cold and salty water to chill them in preparation for packaging. The hot dogs then file down to an unloading zone. Here, a machine pulls them off the bars onto a conveyor. The hot dogs slide off the conveyor into metal containers. If you've been wondering what those black stripes are on the casings, all is about to be revealed, or should we say, unpeeled. The stripe is a marker. When they strip off that casing, the absence of a black stripe means that the hot dog is done and ready for packaging. Inside the peeler machine, a tiny knife slits each casing along the top. Then steamy air blows the casings right off the dogs. This machine peels 700 hot dogs every minute. An inspector checks to make sure the casing has been completely removed and that there are no defects. Then it's into a device that looks like a plastic bicycle chain. The sprockets position the hot dogs for packaging. They manufacture an incredible 300,000 hot dogs an hour. That's close to 2.5 million per shift. So they really do churn them out like it's a sausage factory. Which, of course, it is. Good thing, really. Means lunch shouldn't be a problem. finishing off, we'll be buffing up on gritty abrasive grains and filing the facts on rough sandpaper. See you after the break. Welcome back to How It's Made. It takes true grit to make sandpaper, as in abrasive grains. People have been using abrasive minerals to sand and polish things for centuries. Today these minerals undergo heavy processing to make the grade, or should we say grades, because the grit grades run from very fine to very coarse. Whether you're working on metal or wood, the right grade of abrasive grit can help you polish off the job. They start with bauxite, a naturally occurring mineral that looks a lot like clay. They add alumina, a white powdery material that's actually derived from bauxite. Then they blend the bauxite and alumina with other minerals and release the mix into an electric arc furnace. Here, 3 large electrodes use intense electrical current to heat the mix to over 2000 degrees Celsius. That's hotter than a live volcano. In fact, it looks a lot like lava as the minerals melt and blend together. Standing well back and using a long ladle, a technician takes a sample for chemical analysis. If it confirms that the mix is right, they empty the molten minerals into a big steel pot. The searing liquid weighs several tons, so they use a crane to transport it to a cooling area. "24 hours later, the abrasive minerals have hardened, so they bring in the wrecking ball. It cracks open the hardened mix, which is still quite hot at the core. They drop the ball repeatedly to break up the hardened minerals. They transfer the lumps of abrasive material to a conveyor system. More crushers. These ones have metal plates, break them up into fist-sized chunks. A magnet picks up any excess iron. And then it's into the roll crusher. It rolls them between 2 iron cylinders to grind them to bits. They assemble screens in decreasing mesh sizes to make a kind of shaking sieve. It sifts the mineral particles through the screens to sort them by size. For some perspective, we place a coin against the various mesh sizes. As you can see, only the finest particles of grit would pass through the tightest weave. The bits of grit bounce across the screens and fall into hoppers, a different one for each size. The coarsest grains will be used for rough sanding jobs. The smaller the grain, the finer the finish. The finest grits are microscopic in size. To find out how the coarse abrasives shape up, they funnel them into a cup. Then weigh the grains. A higher weight means they're densely stacked and therefore blockish in shape with blunt edges. A lower weight means they're flat and sharp. They use a different test for the most minuscule grits. They suspend the particles in an electrolyte solution, then apply an electrical charge. This allows them to count and evaluate the grits. Now these abrasive grits are ready to be packaged and shipped out. Making them has been, well, quite a rough job. Coming up, we'll go to the sandpaper factory where they'll get some backing. We'll have the nitty-gritty on that process next. To make sandpaper, you need a lot of grit. There are thousands of tiny abrasive grains on a single piece. The whole idea is to create friction. By rubbing it against wood or metal, you can remove defects and make things look good on the surface. It's ironic that something so abrasive can make things look so smooth and polished. Sandpaper often isn't made from paper at all, but fabric, like poly cotton. They unwind the cloth into a machine with a printing press. Rollers with rubber printers magnetically attached to them stamp product information onto the cloth. The cloth then travels underneath the printing press, where more rollers apply a heat-setting adhesive to the unprinted side. They measure the density of the coating using a computerized system. This confirms that it's been applied correctly. Then, the cloth is pulled underground to the electrostatic pit. Here, the environment is kept hot and humid, perfect for applying abrasive grains to the cloth electrostatically. They pour the grains onto a conveyor belt in the pit. The conveyor moves the grains under the rolling cloth and between electrodes and ground plates. They create an electrical field that triggers a mini sandstorm. Once airborne, the abrasive grains stick to the adhesive-coated cloth and become embedded in it. This electrostatic system allows them to evenly distribute the grains across the cloth. The grain-coated cloth now rolls out of the pit and back up to the next level. A technician cuts a swatch of the sandpaper, then peels away layers and makes 3 different cutouts. One of the cloth alone, another of the cloth with the adhesive coating, and the third, the grain and adhesive coated cloth. He weighs each cutout to confirm that the sandpaper has been formulated precisely to specification. He also examines the gritty surface under a microscope to confirm the grains are standing up evenly. This production run gets the go-ahead, so they move the sandpaper through a 91-metre-long oven. It has 3 different heating zones, each one hotter than the last. The build-up of temperature bakes the grains into the adhesive. The sandpaper is now rough enough, but not quite ready. In the next step, they roll a coat of resin over the gritty surface, binding the grains to the base. After they cure the resin to the surface, they store jumbo rolls of the sandpaper in the warehouse until they're ready to cut them down to size. They slice some rolls into big sheets. These will be made into commercial sanding belts, the kind used in heavy manufacturing. Another machine punches out sanding discs. And at this station, they unwind 4 rolls of sandpaper simultaneously into a machine. It carves them 4 at a time into small rectangles. These rectangles won't be used for sanding, but as grip tape for skateboards. Whether you're a skateboarder, a handyman or both, sandpaper will give you an edge. The real trick is choosing the right grit or series of grits for the job at hand. Otherwise, you could find yourself in a bit of a scrape. So, if you want to do your level best, need to know the frank facts about frankfurters, or want to polish up perfectly, now you know how it's made. Today on How It's Made. Ice cream treats. They sure take a licking. Wooden golf clubs. Different strokes for traditional folks. Aircraft wings. Their construction, plain and simple. And car battery recycling. On this production line, they really get the lead out. But first, before refrigeration, ice cream was a handmade luxury. They placed the ingredients in a mixing bowl, in a tub filled with ice and salt water. The salt helped the ice absorb heat, cooling the mixture below freezing point. In the 1920s, commercial freezers made mass production possible, launching the ice cream industry. To make those ice cream treats, you must first make the ice cream. It all begins with fresh cream. The factory stores the cream in refrigerated silos set to a constant 4 degrees Celsius. The silos feed a high-speed mixer that blends it with other ingredients. The main dry ingredients are powdered skimmed milk and plant-based stabilizers and emulsifiers. Stabilizers prevent the ice cream from crystallizing, and emulsifiers allow the mix to bond with air during the whipping process. The other ingredients are sugar and corn syrup. After about 3 minutes of mixing, a pumping system moves the mixture into large pasteurization tanks. The tanks keep the mixture at 72 degrees Celsius for half an hour, killing any bacteria and activating the stabilizers. Then the factory homogenizes the mixture, a process that breaks up the fat globules, giving the ice cream a smooth texture. They cool the mixture and add concentrated vanilla flavoring. Then they chill and whip everything for about 15 seconds. Whipping blends the mix with air, transforming it from a liquid to a soft solid. Without air, it would come out looking like frozen milk rather than ice cream. The ice cream sandwich wafers are made of chocolate cake ingredients. A filling machine feeds 2 lines of wafers towards an injection pipe in the center. Just as 2 wafers come together, the machine injects 80 milliliters of vanilla ice cream in between. The pipe's head shapes the ice cream into a rectangular slab that fits perfectly between the wafers. All this happens at the rate of 140 ice cream sandwiches every minute. As the sandwiches move onto packaging, the filling is still ice cold from the freezing phase, so there's no threat of it melting. The packaging system raises each sandwich into a wrapper, then folds and tucks the ends. The next machine counts the sandwiches and inserts them in boxes. Once sealed, the boxes go directly to a storage freezer at -30 degrees Celsius. On another line, ice cream cone production is underway. A feeder drops pre-wrapped sugar cones into holders on a conveyor belt. They first pass under sprayers that coat the inside with a chocolatey coating, which adds flavour and creates a barrier between the cone and ice cream, so the cone remains crispy until you eat it. Next, nozzles squirt in the ice cream filling, 78 millilitres per cone. One production line, 2 flavours. One row of cones gets vanilla ice cream. The other row, chocolate. Now for a tasty surprise in the cone's core, an injection of liquid caramel. This factory also makes ice cream cones with chocolate and strawberry sauce inside. Nice. Next, a chocolate-flavoured liquid topping. Then the crunchy finishing touch, a layer of chocolatey coated puffed rice. Finally, the cones move under a lid dispenser. It applies a wax-coated paper lid to each one. A heating element instantly melts the wax, sealing the lid to the cone's paper sleeve. From here, the ice cream cones go into boxes, then straight into the freezer, ready to take a good licking. High-tech metal golf clubs are now par for the course. But don't count wooden golf clubs out of the game yet. Wooden clubs are all about tradition. Golfers have played with them for centuries, and some still prefer the look and feel of wooden club heads any way you slice it. And I often do. With a good-looking wooden club, your luck could be on the upswing. Each club starts with a log of persimmon wood, which is a type of ebony. They slice it into quarters and discard the centre section because it's lower quality. They cut one of the quarters down to a workable size and shape, then lock it into this duplicating machine. Overhead, they place a more sculpted piece of wood called a master model. As they turn, a wheel traces the contours of the master model and guides a blade below, which carves the rough chunk of wood into a duplicate of the master model. They switch master models to one that looks a lot more like a golf club head. Again, the blade below copies the shape. They cut off the stub of the duplicate and they smooth it with a light sanding. Next, using a spinning cutter, they carve a generous slot into the face of the club head. They spread heavy-duty glue into the slot. Then they plug it with an insert made of rigid plastic. The insert will protect the wooden club head from the force of the golf ball. They trim off the overlap, and then they sand it until the plastic insert blends seamlessly with the wood. Next, using a router, they carve an hourglass shape in the bottom of the golf club head. This big slot will hold the sole plate, which will add weight and protect the bottom of the club. The club head can't be more than 3 grams off the target weight, so they add a lead pellet to make it a little heavier, after factoring in the weight of the sole plate that's still to be installed. They drill an extra hole in case they need to add more lead later. Then they press fit the lead pellet to the club head. They slather adhesive in the slot for the sole plate, then install the sole plate, which is made of stainless steel. Again, sanding smooths away any bumps and grooves. With a drill, they bore a hole in the neck of the golf club head. They slide a glue-coated metal sleeve into that hole. Then they taper the neck with a sanding belt. Using a jeweler's saw, they score the face of the golf club head. These lines are strategic. They'll help give the golf ball spin. They dip the club head in a water-based stain that soaks into the wood but doesn't penetrate the metal sole plate. Then things get messy. They rub paste all over the golf club head, plugging the open pores of the wood. It's a crucial step that will allow them to achieve a mirror finish later. They number it to identify it as a fairway club. Then they give the sole plate a good scrubbing with steel wool to get rid of any fingerprints. They spray it with 5 coats of polyurethane. They push the glue-covered end of the shaft into the sleeve in the club head. They adjust the weight by inserting some pulverized lead in the extra hole drilled earlier. For a player to hit balls accurately, each club in the set has to feel as if it's the same weight. So there's one more weigh-in before they decide this wooden golf club is up to par. Now it's time to hit the course, because winning could be a matter of knocking on wood. It's normally trees in my case. 4. Coming up after the break, aircraft wings, manufacturing that gives us all a lift. And car battery recycling, production line pollution prevention. See you after the break. Welcome back to How It's Made. Aircraft wings provide the lift that takes us to the skies. They're designed to be light, yet very rigid. Producing them requires a strategic balance of old-school production methods and high-tech computer-assisted design. The wing's frame is made up of 3 main components: the rear spar, the main spar, and ribs. They make the ribs from aircraft-grade aluminium. It's corrosion-resistant and has great tensile strength, allowing it to resist extreme pressures. A computer-guided stamping machine punches holes for rivets and control cables. It also stamps larger holes to reduce overall weight. Workers break attachments called micro-joints and extract the ribs. Each rib now goes onto a metal and rubber forming die. A hydraulic press applies 150 tons of pressure, stamping the rib to the die shape. Using a grinder, workers smooth out the sharp edges the stamping process left behind. Then they peel off a plastic film that protected the ribs from scratches until now. The factory uses the same process to construct the main spar. The spars run the entire length of the wing. It takes even more pressure this time, 220 tons, to bend the spars into shape. That's because this aluminium is 3 times thicker than that used for the ribs. To ensure they've aligned the ribs perfectly for riveting, workers manually push spring clamps into the spar. These hold the ribs in position. Workers now hand drill holes for larger rivets, then smooth out the sharp edges with a deburring drill. Then they use a pneumatic riveting gun and bucking bar to rivet ribs to the main spar. They use a smaller bucking bar for some of the tighter spaces. The completed airframe now goes on a positioning rack to receive an aluminium covering they call the wing skin. Workers use spring clamps to position the aluminium top skin onto the airframe. They use the same procedure for the leading edge wing nose. Once everything's held together with spring clamps, workers permanently rivet the assembly. Meanwhile, welders fuse the wing's fuel tank using an argon gas torch. Argon contains fewer contaminants than the typical acetylene torch. They fit the tank into the wing chamber, then secure it by bolting steel belts onto the spars. Now they position the tank's covering plate and screw it onto the wing. These holes are for fuel lines and control cables, which run the entire length of the wing. The wing tip is the final piece they fit and bolt onto the wing. It's made of a lightweight fiberglass and plastic composite. The completed wing is now ready to be bolted onto the aircraft body. Just one aircraft wing weighs a mere 79 kilograms. But it's certainly no lightweight when it comes to strength. It can withstand nearly 2,500 kilograms of pressure. Up, up, and away. Car batteries may die. But that doesn't mean it's the end of the road for the components. These lead-acid batteries are routinely recycled. This keeps toxic materials out of landfills, and it means we get a lot more mileage out of those old car batteries. This battery may be toast, but it's not trash, because dead car batteries are jump-starting a major recycling industry. Pallets of old batteries are tipped onto a conveyor. It takes them up into an enclosed machine that has over 30 rotating hammers. They smash the old batteries to bits, and then a screen filters out the lead-acid paste. The broken bits of lead and plastic tumble into a big vat of water. The lead and other metals sink, while the lighter plastic pieces float to the surface. This system allows them to sort and separate the battery components. The plastic pieces have been cleaned, and a machine now blows them into the back of a truck. They'll be taken to a plastic recycling plant and turned into pellets that will eventually be used in the production of new car batteries. A worm screw now moves the lead and other metals to another part of the plant to await further processing. The acid from the lead-acid paste screened out of the batteries earlier has been neutralized and turned into water. This press squeezes the water out, so all that remains is a lead paste. They remove it and add it to the pile of lead and other metals. The water from the deacidification process contains some metallic residues, so they treat it with chemicals that cause the contaminants to precipitate and then settle into a sludge on the bottom of the tanks. They sample the water to make sure the particles are settling properly. They pump out the sludge and then filter the water, which now meets regulation standards and can be poured down the drain. The sludge goes into the pile of lead and other metals. They add refined coal to the pile as a processing aid. Then the battery solids head up a conveyor into a revolving dryer. The metals spend 20 minutes in here to remove any excess moisture. Then it's into a furnace for 10 hours. The lead melts into a liquid and the other metals float to the surface, allowing them to be skimmed off. The molten lead goes into a steel kettle, where it's mixed with caustic soda. This causes some remaining contaminants to float to the surface so they can be removed. The liquid lead is now fairly pure, so it's time to pour. They pump the lead into molds and skim off any lingering impurities. Below, a constant spray of ice-cold water chills the molds, and the lead hardens into bars in just 4 minutes. The conveyor winds downward, and the bars are tapped free of their molds. There's enough lead in one of these bars to make 3 car batteries. They'll be remelted and moulded into battery components, and the final product is as good as new, proving that recycling can get new life out of that old car battery, and in the process give a boost to pollution prevention efforts, which is a positive. So, if a frozen feast tickles your fancy, or you want to swing some traditional wood, the next time you take to the skies, you'll know how it's made. Today on How It's Made. Automotive fuel pumps. Without them, we'd be running on empty. Cricket bats. It don't mean a thing if it ain't got that swing. Change machines. Ka-ching, ka-ching, to coin a phrase. And ductile iron pipe. How it's made goes underground. But first, when you start your car, it activates a pump that's usually located inside the fuel tank. This electrical pump pushes the fuel out of the tank to injectors, which aerate the fuel and deliver it to the engine's cylinders. Without a pump to get fuel flowing, well, you'd be going nowhere. You might think that submerging an electrical pump in gasoline would be a risky thing. But because liquid fuel doesn't explode on its own, it's actually a very safe place to put it. They begin with the pumping mechanism, sandwiching a gear and several rollers between 2 metal plates. The rollers will rotate to pull fuel into the pump and then push it out. They test each roller assembly by spinning it from the bottom. A robot then pops it out and moves it to the next station. Here they attach the electrical motor to the roller pumping mechanism. Then they slide a magnetic sleeve over the assembly and cap it. All the parts that make up the pumping mechanism have now been assembled. Next, they install an end cap that includes a filter made of metal mesh. They slide a metal sleeve over the pump unit and press fit it together. Inside this special chamber, large magnets generate a very strong magnetic field. The magnetic force field actually causes the metal sleeve to collapse. This crimps the sleeve at one end, holding everything together. Next, they place retainer rings in slots in the fuel pump cap. They place a metal bracket over the pump. The bracket steadies it and serves as a guide as they install the brushes and coils which will supply electricity to the fuel pump motor. They slide a brass terminal onto the end of each coil and brush assembly to facilitate the electrical connection. Then they press fit the terminals to the assembly so they're firmly attached. When the job's done, a robot removes the bracket. They've built this fuel pump from the inside out, and now the actual workings are complete. They hook each pump up to a power source and run fluid through it to test the pumping action. Then they check for proper flow and pressure. If the pump passes inspection, a robot sends it down the assembly line, where they assemble the system of tubing that will carry the fuel to the engine. They seal the joints with a brazing paste. Then it's into a gas oven that bakes the brazing paste, causing it to harden and fuse to the tubing. They remove the tubing from the oven and brush off any unwanted bits of metal and hardened paste. They cap the tubing to keep dirt and debris out as a packaging precaution. Now they hook up some rubber tubing to the pump and secure it with metal clamps. They link it to the rest of the piping and hoses. They wire the fuel pump and hook up a connector to attach it to the engine's wiring. This is the sending unit. It's a float with a metal arm that's attached to an electronic sensor. The sensor sends information about fuel levels to the fuel gauge on the car dashboard. They use a computerized system to check the sending unit's accuracy as they move it up and down. Now this pump is ready to handle the highs and lows of the fuel tank, and it's time for us to hit the road. References to the game of cricket date back to the 1300s. Historians believe it started as a children's game. In the 1600s, working men began taking up the game as a pastime, and before long it caught on with the upper classes. By the 18th century, cricket was a major organised sport in England. Cricket bats are made of a particular species of white willow. It has stringy wood fibres that are unusually long. These give the wood elasticity, the key to its performance. Bat makers use as much sapwood as possible. It's moister than the heartwood at the tree's core because sap runs through it. Production begins with willow pieces 3/4 of a metre long. The first machine trims them down roughly to size. A few sprays of water limber up the wood fibres. Then each piece goes through a pressing machine 3 to 4 times. A curved roller applies up to 3 tons of pressure, rounding the bat's face and compressing the wood by up to a centimetre. This pressing is essential because it determines the bat's performance and durability. The bat maker draws a V on the end, where the bat handle will attach. Then he removes the bulk of the wood behind the V on a table saw. This minimises the amount of work he'll have to do later by hand. Now he cuts out the V. This creates a joint in which to insert the handle. The handle is made of cane, dried vine stems, glued together in sections and coated with rubber. The end the player grips has been shaped on a lathe. The other end will attach to the blade. The bat maker cuts the block-shaped tip into a wedge that'll fit into the V-cut, then glues the 2 pieces together. A few taps with a hammer ensures a tight fit. He spreads the glue that oozes out all over the joint to seal it. Now he shapes the profile, using a classic woodworking tool called a draw knife. This only takes a few minutes but requires years of experience and an expert eye. Then he completes the shaping with another pressing to curve the bottom third of the bat. International cricket rules regulate the length and width of bats, but there's no restriction on curve. Getting this right is tricky though. Too much curve and he'll harden the blade, losing performance. The bat maker finishes off the shape using specialised craft tools. Then he uses a metal hand plane to flatten the blade's edges. He ensures the bat has good spring by hitting it with a dense wooden mallet. He also analyses the sound of the strike. The softer the sound, the softer the wood, and the better the bat will play. He smooths the bat against a drum sander. The air-filled drum moulds to the bat, so it doesn't wear away the shape he works so hard to achieve. Then a worker smooths out the rest with a belt sander custom-made for the bat's shape. On each machine, they sand the entire bat twice, first with a coarse abrasive, then with a fine one. Next, they mount the bat on a binding machine and coat the handle with glue. Twine wrapping binds together the rubber-coated cane sections that make up the handle. They apply extra glue to prevent the twine from unravelling. Next, they polish the blade against a cotton wheel. Once the wood is shiny enough, they stick on decals with the bat's brand name. Then slip a rubber grip over the binding to prevent the player's hands from slipping. The bat's 2 main materials complement each other when striking the ball. The willow wood blade flexes enough to deliver a good hit. The cane handle absorbs that energy, protecting the player's hands. How's that? Coming up after the break, those clever coin-counting machines, and going underground with ductile iron pipes. Join us after the break. Welcome back to How It's Made. Change machines were invented in the mid-1950s. Vending machines were becoming more popular, driving a need for change. They began as simple mechanical coin changers, converting large coins into smaller change. Today's modern machines can convert £20 notes. Times sure have changed. It's like magic. In goes the note, and hey presto, out comes the exact change. But there's no sleight of hand, just innovative design and some pretty high-tech equipment. Production begins with the machine's cabinet. A computer-guided laser cuts the cabinet parts from a sheet of steel measuring 1 by 1.5 meters. Workers shake the parts free and push out the openings in the panel that will become the cabinet's front door. They shape the parts in a machine called a press brake. This is one of the door panels. The machine forces it against a die, bending the edge. These bent edges will strengthen the door and help it fit snugly into the frame. The laser cutter also makes a series of holes in another cabinet part. Then workers press threaded studs into the holes. A vibrating feeder dispenses the studs into the insertion machine they use. Now they bend the sheet, again using a press brake, and make the three-sided panel that will become the cabinet's sides and back. To that, they attach the top and bottom panels. Then they set it in position on a computerized welding station and rotate the table. A robot makes precision welds behind a steel partition that shields the worker from heat and harmful rays. Now they assemble the change machine's coin dispenser. It has 2 counter-rotating discs fitted to the diameter and thickness of a coin. They work together to seize and align the coins, then drop the change into the coin chute. Workers set in these metal discs and a plastic gear mechanism that rotates them. Then they secure the parts on a fixture and drill holes into the gear mechanism. Next, they insert roll pins to hold the parts together. The coin discs, if properly assembled, will spin freely. Now workers can assemble the coin dispenser discs and gears. This is precision work. First, they set parts in a metal casing. Plastic rings go around the discs to guide and support the gears. Then they attach the gear train motor that powers the discs that dispense the correct change. A plastic guide on the casing helps the coins drop in properly. Next comes the coin chute that guides the change out of the dispenser into the machine's coin cup. The dispenser holds up to 500 pounds, which can weigh a hefty 20 kilos, so they add a handle, which locks in with this tool called a ring fastener. Now it's time to put it all together. First, they install the electric power supply on the inside back wall. Next comes the note validator and the coin cup. Then the coin dispenser and electronic control board, the brains of the machine that calculates the change. Finally, on goes the instruction information. So how does it all work? Let's open the door and see. First, the note acceptor scans the bill's paper and ink, then stacks it in a box. Then ka-ching! Out comes the exact change. Chances are you use ductile iron pipe every day and don't even know it. The underground pipes that bring you drinking water and take away household waste are cast from ductile iron. Ductile iron is more flexible than ordinary grey iron. Under pressure A ductile iron pipe will bend before it will break. Ductile iron pipes are made of 90% recycled metal and have a lifespan of hundreds of years. Production begins in the pipe factory scrapyard. These old cars are on their way to a shredder that chews them up into small bits. The factory sorts by material. It discards the plastic, sells the aluminium and copper, but keeps the steel and iron. The factory also gets scrap steel from demolished buildings and other sources. After analysing the chemical composition, it sorts the shredded metal accordingly. The crane operator uses an industrial magnet to gather a specific weight of each type of steel and iron. The shredded metals go into a blast furnace, fueled by coke, a form of coal. At 1,400 degrees Celsius, the iron and steel liquefy, while impurities are carried away. Workers then add magnesium. This turns the metal from ordinary grey iron into stronger, more flexible, ductile iron. The molten iron travels down a trough into a casting machine. It enters a spinning mould. Centrifugal force spreads the iron against the mould walls. A cooling system chills the walls so the iron solidifies within seconds. Then an extractor pulls out a 6-metre cast iron pipe, the standard industry length. Before each casting, workers insert a round form, called a core, into one end of the pipe mould. Iron fills the void between the core and the mould, forming a flared edge, called a bell. The core also seals off that end of the mould, preventing molten iron from flying out during the casting. To connect pipes, installers fit the bell of one pipe over the straight end of the next one. A rubber gasket seals the link together. They can make pipes of different diameters with the same casting machine by changing the size of the mould inside. After extracting the pipe, the factory weighs it and measures the wall thickness to ensure everything meets specifications. Then, on the bell end, they remove the core. It's made of sand and plastic resin, so it simply disintegrates. This factory makes pipes in several diameters, but regardless of size, the casting process is always the same. It just takes less time with smaller pipes because they solidify faster. A freshly cast pipe is about 800 degrees Celsius, but as soon as it leaves the mould, it cools quickly. Such rapid cooling makes the iron brittle, so the pipe goes directly into a gas-fired annealing furnace that reheats it to 930 degrees Celsius. This alters the internal structure of the iron, making it flexible again. The pipe then runs through a cooling chamber that showers it in cold water. To prevent the iron from corroding, they spray the inside with cement, building up a lining 3 millimeters thick. Then they smooth it out by spinning the pipe for a few seconds. They paint the entire pipe inside and out. That seals the surface, enabling the cement to cure over the next 24 hours. It also provides some extra rust protection. Finally, a robot paints a stripe around the straight end of each pipe. This is a depth guideline to let the installation crews know when they've inserted the straight end of one iron pipe as far as it can go into the bell end of the next one. So, if you're running on empty and need to fill her up, or fancy a nice clean stroke through the covers, or you simply decide it's time for change. Now you know how it's made. Today on How It's Made. Wooden barrels. Production's on a roll. It's Super Cooper. Fire hydrants. We'll hose you down with the details. Automotive seats. Making them is a cushy job. And cathode ray tubes. We monitor their production. But first, in the old days, wooden barrels stored all kinds of goods for the simple reason that they were easy to move. If you couldn't lift them, you could roll them. Today, modern machinery has made barrels obsolete, except for storing fine wine and spirits. And so the time-honoured tradition of barrel making lives on. These wooden barrels are for storing whiskey. They're made from American white oak, cut into pieces called staves. The staves go into a planer that shaves them to 2.5 centimeters thick. Next, a machine punches 2 6mm holes on either side of each stave. Dowel pins made out of hickory, a very strong wood, go into these holes to hold the staves together. They take the staves, place them on a guide, and press them together. A smaller piece completes the shape. Now it's onto the rounder, a machine that cuts it into a circular shape. This creates the barrel's lid, or head as it's called. And since 2 heads are better than 1, each barrel has a pair. The barrel head now goes onto a contraption called the char tunnel. Its gas burners scorch the wood. This charring not only changes how the natural wood looks, it also gives colour, flavour and aroma to the whiskey the barrel will hold. They coat the head's edges with liquid beeswax, which helps them set it snugly into the barrel body. They run the staves against this machine to narrow their ends. This gives the barrel its characteristic shape, with a smaller radius at the ends than in the middle. At the barrel raising station, a worker positions an iron hoop and starts to assemble the barrel inside it. He selects staves that vary in width in order to use as few as possible. This reduces the number of joints and therefore potential leaks. He gently lassos the barrel together. If he pulls that dry wood too tight, it'll break into pieces. A loose hoop gives the wood room to expand. Next, the barrels pass through a steam tunnel for about 15 minutes, adding moisture to the wood so it can flex without snapping. Workers pull out the barrel and remove the top and bottom hoops. They replace them with sturdier ones and hammer them in. Without these hoops, the barrel would spring apart like a jack-in-a-box. Next, 2 more hoops around the body. The wood groans from the intense pressure that forces the staves together, but there can't be any gaps between the staves or else the barrel would leak. The barrels pass over a gas burner that blasts a flame inside each one to char its interior. Seconds later, water shoots into the barrel to put out the flames. An automated saw cuts a V-shaped notch in the top and bottom of each barrel. This is where the barrel head will slot in. A fan blows away the sawdust. Now a machine removes the iron hoop on each end. A worker pours in a gallon of water to cool the barrel, still hot from the charring process. Then he puts on a barrel head and a stronger permanent iron hoop on both ends. Now machines remove the two iron body hoops and also replace them with stronger ones. These barrels hold their shape by sheer pressure. There's not a drop of glue used to hold them together. The gallon of water is still inside the barrel. Workers drill a hole in the side, then plug it by hammering in a rubber stopper with a spout. An inspector checks the barrel for leaks, stamps it approved, and labels it with a barcode for inventory. They remove the stopper to release the gallon of water, which has since turned to steam because of the heat. The barrels are now ready to go onto the distillery, where they'll get their fill of some fine Kentucky whiskey. Fire hydrants have been in use for more than 200 years. In the old days, their main purpose was to supply water to fight fires, but they also provided the public with a handy water supply. Fire crews rely on the nearest hydrant to be ready at a moment's notice to help them douse the flames whenever they break out. Fire hydrants are essential to every community. They need to be instantly recognizable, easily accessible, and simple to operate. The ones in residential areas are designed to deliver no less than an impressive 5,700 litres a minute. The hydrant making process starts with recycled scrap iron along with steel and raw iron. Using a magnetic crane, workers load the metals into a furnace and melt them at 1,538 degrees Celsius. This turns the scrap metal into molten iron. Then they transfer the molten iron into a remote-controlled ladle and empty it into an automated pouring system. To cast the hydrants, workers first make a two-part mould by compressing a mixture of sand and bonding materials. One part, called the mould, forms the hydrant's exterior shape, while the other part, called the core, forms the interior shape. An automatic core setter positions a core in each mould. Then a conveyor advances the mould under the pouring box, which fills the cavity between the mould and the core with molten iron. After the iron cools and solidifies, the moulds enter a tumbling barrel. As they revolve, the sand gradually disintegrates, freeing the iron casting inside. Workers drill and thread the hydrant casting to prepare them for assembly. Then they pre-assemble and paint them the colour the customer requested. The fire hydrant's internal workings, called the valve assembly, allow water to flow through when opened. A series of rubber O-rings on the main valve will prevent leaks when the hydrant's closed. Now the hydrant is ready for final assembly. Workers attach the nozzle section to the top of the hydrant barrel and attach nozzle cap chains with a crimping tool. Using a torque wrench, they attach cast iron safety rings. These rings are designed to disengage the top from the bottom of the hydrant so it doesn't get damaged if a vehicle hits it. Workers clamp the water main connector into place and pressurize the hydrant to normal city pressure to check for leaks. Using a hoist, they lower the pre-assembled nozzle section over the stem and fasten it to the water main connector with stainless steel bolts. They lower the bonnet into place, bolt it to the nozzle section, then open the hydrant for a high-pressure test. They turn the operating nut to allow water to flow through. Before conducting this test, they force out the air inside the hydrant with water. Workers transfer the finished hydrant to a pallet and apply final paint touch-ups. Some fire hydrants that were installed more than 100 years ago are still in use today. Splashing. Coming up after the break, sit back and enjoy the ride with comfy car seats. And monitor the situation on a CRT. See you after the break. Welcome back to How It's Made. When it comes to the seating in our cars, perhaps we should sit up and take notice. It's come a long way since the car was invented in the 19th century. Back then, seats had no springs and not much padding, so you could feel every bump in the road. In today's car seats, we have a much easier ride. Padded and belted, modern car seats are a real comfort zone. They manufacture the components separately and ship them to this factory for assembly. They arrive as needed on the production line, so there's not a lot of stockpiling. It means the flow of parts into this plant is constant and organised because they make over 400 seat variations here. They cart the parts to the assembly line in the order they're needed. On this line, there are 60 workers, each with specific tasks to perform. They receive a build ticket for each part and scan it. This allows a central computer to track production and verify that the right parts are being used to build the right seat. An operator tucks the seat warmer pad and cables into the cushioning for the bottom half of the seat. She loosely places the fabric over the assembly and attaches it with wire. Then it's over to the next station, where the operator completes the upholstery job. Each worker has just 88 seconds to perform his or her task, so there's no sitting down on the job. They install a seat warmer system on the backrest section of the seat and cover it. They slide an airbag into a special sleeve. These seats come with springs that clip onto their metal framework to provide lumbar support. They fit the cushion assembly on the springed framework and pull it tight. They smooth out any wrinkles. This is called finessing, and they install the headrest. Next, they tackle the lower framework. They equip it with a mechanism to adjust the height of the seat. Electrical connectors go in next. Then they bolt the lower framework to the cushioned backrest. They attach the pre-tensioner apparatus, which locks the seatbelt in position, then wire the connector box. They fit the lower cushioning on the framework and add the recliner spring. A plastic valance makes it all look neater. It's time to take this driver's seat for a test run. They hook it up to a power source and check if the airbag and seat warmer are operational. They iron out all the wrinkles because the car manufacturer will reject any seat that's less than perfect. And then slide and tilt the seat to make sure the adjustment mechanisms are working properly. They assemble the rear seats using the same techniques. Again, each operator gets exactly 88 seconds to complete his or her job. When you add it all up, an entire seat set takes just 62 minutes to assemble. Before they ship the seats to the car factory, they take a photo as a production record. It proves each set was in perfect condition when it left the factory. Now these car seats are ready to hit the road. They strap them onto delivery pallets and load them onto a truck, 60 sets at a time. They'll arrive at the car plant just as the vehicles they're made for are rolling off the assembly line. Once they're installed, all you need to do is sit back, fasten your seatbelt and enjoy the ride. The CRT, short for cathode ray tube, produces the images that we see on our TVs and computer monitors. The ones that aren't LCD or plasma, that is. The cathode ray tube was invented back in 1879. A CRT is made up of two main components, a large glass bulb and an electron gun. CRTs start with a molded glass bulb. First, workers remove microscopic debris using a high-pressure water rinse. Hydrofluoric acid is then sprayed to clean the glass at an atomic level. They pour a phosphor solution into the bulb. Phosphor is an organic compound that emits light when struck by electrons. The phosphor particles settle and form a chemical bond with the bulb face. Workers pour off the excess solution and clamp the bulb over a nozzle that sprays clear lacquer. The centrifugal force guarantees an even coat over the phosphor to protect it for the next step. He paints a conductive coating over the anode button, which will provide a flow path for the electrons that light up the phosphor particles. Next, a worker drops an aluminium pellet into a tungsten coil. He places the bulb over a vacuum device and draws out the air. Then he applies an electrical current to the coil. It evaporates the aluminium pellet, which spreads a mirror-like coating on the inside of the bulb. Now they heat the bulb to 218 degrees Celsius for 1 hour. This bakes out the lacquer and any trace of moisture. Using a high-temperature flame, a worker aligns and fuses a glass neck to the bulb. Then he paints it with the same conductive coating. This assembly is part of the electron gun that goes inside the bulb. It shoots electrons at the bulb's phosphor particles that lights them up, creating the images we see on screen. Workers stack the grid cups that focus the electrons on the screen, then using beading glass, align and fuse them into position. Robots heat and affix the beading glass to assemble the electron gun components. They cool off the gun with pressurized air. Once cool, a worker builds up the gun and inserts the completed gun assembly into the bulb. Next, he positions the bulb on a glass-blowing lathe and cuts excess glass away from the neck. Using a graphite paddle and a high-temperature torch, he mates the glass neck to the electron gun's stem. This ceramic heating coil melts that green glass pellet to keep the bulb under vacuum. The tube is heated to 400 degrees Celsius for 2 hours, and once again, a vacuum is drawn. To minimize image flicker over the tube's lifespan, workers condition the bulb using a high-voltage coil. It smooths any rough surfaces that might remain on the electron gun. Finally, workers apply electrical connections and bring the cathode ray tube to life. So, if you fancy rolling out the barrel, or you feel the need to douse an old flame, well, you can sit back and enjoy the ride. Because now you know how it's made. Today on How It's Made. Stainless steel. Its reputation is untarnished. Football helmets. We put our heads together to bring you this story. Resin figurines. A whole cast of characters. And laboratory glassware. Witness a real test tube birth. But first, stainless steel was invented in the early part of the 20th century. The key ingredient is chrome, which forms a protective oxide film on the surface. Originally, people were amazed that cutlery made from it didn't need to be polished. Called non-rusting steel, it was the talk of the dinner table. Stainless steel can be made to look shiny and new, even when they start with scrap. They recycle stainless steel, giving old sinks, pots and a whole range of other things a new lease of life. They feed tons of scrap steel into a roaring furnace, along with chrome and nickel alloys for added strength and rust proofing. Enormous electrodes heat the mix to melting point, and the show rivals a firework display. After several hours, the molten mix goes into a refining furnace. Pipes blast argon gas and oxygen up through it. This converts some impurities to gas and causes others to float to the surface so they can be removed. A technician checks the temperature and takes samples to make sure the chemistry is right. They add scrap to bulk up the mix as it melts. The scrap also causes a chemical reaction that helps to fuel the refiner. The bubbling steel soup now flows out of the refining furnace, and rollers guide it as it's cast into a long mould. The result is a 70-metre-long ribbon of steel. Torches cut it to shorter chunks called slabs. A worker writes identification information on each one, using chalk that works on hot surfaces. They hoist the slabs over to another station to await further processing. After this break in production, they reheat the slabs to soften them up. A rusty scale has accumulated on the surface of the steel. They pressure wash it away without cooling the hot metal. Now the slab shoots back and forth through a machine with rollers. A constant spray cools the rollers as they stretch the steel longer and thinner. It's now over 600 meters long. They spray water on the stretched steel to cool it a little, but not too much, because it needs to be soft and flexible enough for coiling. This spool coils the strip tightly, like a roll of toilet paper. Then they transfer the roll of steel to another station. Here, the steel goes into a hot acid wash that removes scale that's built up since the last cleaning. Burners in this machine also heat the steel and then slowly cool it. This relieves stress in the metal, softening it for further processing. They now unwind the steel into a machine that rolls it thinner so that it's exactly what the customer ordered. Rolling the metal when it's cold also causes it to harden and makes the surface pores close so it shines. One last cleaning and the stainless steel strips look spectacular. The chrome in the steel combines with oxygen in the atmosphere to form that oxide film that prevents it from rusting. Finally, rotating knives trim the edges and slit the steel to various widths, again to meet customer specifications. The job is now done, and it's a brilliant finish. Indeed. American football helmets cushion the cranium, helping players score touchdowns without losing IQ points. Helmets have been part of the sport for over a century. At first made of leather, they switched to padded plastic helmets in the 1950s. And they've turned out to be great shock absorbers for the skull. In a game of tackles and tumbles, a helmet is essential equipment. To make one, plastic pellets are drawn into a machine that melts and molds them into a helmet. This fist-like device shapes the inside of the shell. It takes just seconds for the shell to harden. A robot collects it and transfers it to a conveyor. It's quite a lineup. The shells move into position for a trimming. They clip off plastic left over from the moulding. Next, a robot drills up to 9 holes in the shell. The holes will be used to attach a liner, face guard, and various pieces of hardware. This robot works far more quickly than a human can, performing all the drilling in just 30 seconds. It's programmed to be extremely precise, doing a flawless job with computerized precision. Then the robot flexes back to receive the next shell. A worker collects the drilled shell and moves a new one into position for the robot. They rough up the outside of the helmet shell with an orbital sander. This prepares it for priming and painting. The shells spin as they spray them with paint. It's a high-grade car paint. They get 3 coats because this paint job will have to be rugged enough to survive the game of football. The helmets dry in the open air for up to 18 hours. A chemical reaction occurs, causing the paint to harden to a glossy finish. Not every helmet is painted. Sometimes football teams prefer tinted plastic. It all depends on the look the team is going for. They attach labels, including cautionary information, trademark logos, and the date of production. The padding is made of vinyl and foam. They snap it in place in the crown of the helmet. The padding for the side and back is made of the same material. They reinforce the back with a plastic bumper. A helmet from each production run undergoes an impact test. The helmet has been fitted on a head-like form, equipped with sensors. The technician calibrates the sensors using a computer. He presses a button, and the helmeted head falls. This mimics the effect of a player's head hitting the ground in a tackle. The computer then measures the force of the impact on the dummy head. Once the production run gets the OK, they attach the face guard. It's made of plastic-coated steel and has been custom produced at a different factory. There are dozens of face guard styles for the player to choose from. This helmet is now looking pretty fierce, but it's not ready for action yet. It needs a chin strap and cup. This machine uses heat to transfer a foil logo onto the polyester chin straps. It also cuts them to the correct length. Once a chin cup has been sewn to the strap, they fasten the assembly loosely to the helmet. Later, it will be precisely fitted to the player. This helmet is now almost ready for kickoff. There's a final inspection, and then they wrap it up, complete with a manual and fitting instructions. It's taken less than a day to manufacture this helmet. It's designed to withstand thousands of impacts, because in the game of football, protection against head injury is a crowning achievement. 23-41, Coming up after the break, resin figurines, a model of production. And laboratory glassware, test tube technology. Join us after the break. Welcome back to How It's Made. Figurines come in many materials, from porcelain to plastic to resin. Not the kind that comes from trees, but a synthetic resin, a kind of plastic. It's affordable, lightweight and easy to use, making it the model material of choice for many artists and craftsmen. Each figurine in this collection is cast from a mould of the original sculpture and then hand-painted. This character is an actual 19th century federal marshal. Working from period photographs of her subject, the artist makes a sketch she'll use as a model. She needs plastic-based clay, so it's easier to sculpt. She works in the facial features, referring to the photographs to create a true likeness. She usually starts with the figure's head and then adds it to the body. She works from more photographs to create his rifle. It's a delicate piece, so she sculpts it separately before setting it onto the figure. Barring her signature, it's now ready for casting. First, the sculpture bakes for 30 minutes at 135 degrees Celsius to harden it. Then workers cover it with a thin layer of releasing agent so it won't stick to the production mould they'll now make. They place a wall around the piece, tightly seal the base to prevent leaks, then pour in a silicone rubber mix. In 2 days, the rubber hardens enough to hold the shape and the details of the sculpture, but it's still flexible enough to enable workers to remove the original artwork without damaging anything. After removing the retaining wall, they use suction to gently pull the piece from the mould cavity, which retains the sculpture's shape down to every last detail. Now figurine production can begin. Workers fill the mould cavity with a mixture of resin and flour made from ground pecan shells that colours the resin and makes it stronger. The mixture sets in less than an hour, and out comes the first of many figurines, a perfect replica of the original artwork. They sand the base to level it. Then they stamp it with the figurine's name, an ID number, and copyright information. Resin is an ideal material for casting because it captures all the details of the original artwork. It creates lightweight, durable reproductions that can be finished in a variety of ways. Here, the first artist coats the figurine's broad areas with acrylic paint. Working colour by colour, she uses various brushes depending on the areas to cover. She finishes with the smaller details. Then she passes the figurine on to the next artist. She paints in the facial features and other fine details. She starts with the whites of the eyes, then views the figurine from all angles to make sure she doesn't overlook any tiny detail. Her fine brushwork on the facial features is what truly brings this figurine to life. Bass Reeves, US Marshal, is just one figurine in this series that proudly honours the contribution of African Americans in shaping the history of the United States. Once Marshal Reeves passes inspection, workers wrap up production, so to speak, in protective bubble wrap. Each piece in the series comes with an authenticity certificate, bearing the artist's signature, as well as the name and life story of the person the figurine portrays. Collecting this particular set of resin figurines appeals to more than the knick-knack lover. This is indeed affordable art for the history buff. Small-scale figures that pay a large-scale tribute to African-American pioneers. Their size, shape and function run the gamut, ranging from beakers and test tubes to Petri dishes and vials. Mixing, measuring, storing or sampling, it's all in a day's work for a piece of laboratory glassware, built to withstand even the most potent of chemical concoctions. Many scientific breakthroughs are born here, inside laboratory glassware. The tubes scientists use to hold liquid samples for chemical experiments. They start off as thin glass tubing, stacked by size, weight, length and diameter. Workers select the correct size for the culture tubes they're making and place them in a magazine. As it spins, it drops a tube into each slot on a cutting bed. Then comes the first cut by glass flame. When the heated tubing contacts the wet steel blade, the thermal shock results in a clean separation of the glass. The tubes get a second thermal shock treatment, which cuts them to length. Then it's onto the glazing bed. A glazing burner shoots out flames at a temperature of 650 degrees Celsius. The heat melts each tube at one end, forming a lip called a glass bead. Just 2 seconds of heat splits the tubes into two. The intense heat forces the glass bottom of each tube to close in on itself. The finishing fire smooths out the closure. Then they shoot a small amount of air into the open end of the tube, which forms the round curvature on the bottom. Now the tubes head into an annealing oven, side by side. They bake for 15 minutes at 650 degrees Celsius. This strengthens the glass. The heat also sterilizes the tubes. Once the tubes cool, workers collect and pack them. Here, they're making pipettes, long tubes that labs use to transfer fluids. A flame heats the glass to form an indentation, which determines the flow rate through the pipette. A wider flame then heats the glass, making it soft and malleable. Large rollers tug at the sides, drawing the soft glass to form the pipette's tip. Now for the other end. They cut it to length using thermal shock, and again, a glazing burner forms a glass bead along the rim. A cutting wheel slices through the tip end, creating two tubes of identical length. This production line makes vials. These gizmos, called top turrets, feed large glass tubes into a machine. First, a punch-out burner heats the end of the tube to create an opening. Then a steel pin widens the hole on the upper part of the vial. A forming die squeezes the heated glass to sculpt the shoulder, while a steel plug rises from the bottom to open the vial even wider. Then a second forming die shapes the neck. Next, a parting burner splits the vial into two. A bottom turret plucks the newly created one and draws out the soft glass to lengthen it. Fingers inside the turret prevent the glass from breaking. All that's left now is shaping the bottom of the vial. A burner forms a concave base in less than a second. The vials now slide down to what's called an afterformer machine. Here, suction cups lift and place each vial into metal grooves on a printer bed. It's a basic silkscreen printing process, with a squeegee pushing paint through the screen's holes onto the vial. Grippers now place the vials on a rack headed for the oven, where they'll bake for about 20 minutes. Finally, a robotic arm whisks the finished vials to packaging. From there, it's off to a blood bank, a hospital, or chemistry class. Ooh, that's a vile thought. So, whether your steel lacks luster, or you're a head case who needs protection on the gridiron, fear not, you can figure it out. Now you know how it's made. Today on How It's Made. Fire extinguishers. We answer those burning questions. Donuts. The whole story. Jammy job, that. Shock absorbers. You can't dampen our enthusiasm for this story. And banjos. They come with strings attached, you know. But first, the first fire extinguisher on record was in Europe in the Middle Ages. It worked like a giant syringe, used to squirt water at a fire. The modern extinguisher uses compressed air as a propellant. The fire-dousing substance is either water or a chemical liquid, powder or foam. Squeezing the lever opens a valve that releases compressed air. The pressure propels a chemical through the hose and out the nozzle. To make the release valve, they start with cylindrical aluminium, called blanks. A carousel runs each one through 16 different machining stations. At each stop, under a shower of lubricant, tools shape the blank for 6.5 seconds. As each blank completes the circuit, it comes off the carousel. From blank to valve in 1.25 minutes. Now they rivet the fire extinguisher's aluminium handle onto the valve. It pivots on a pin. Next, they rivet an aluminium lever onto the handle. This is the lever you squeeze to use the fire extinguisher. Then comes the valve stem, the valve's inner workings. Workers simply place it inside, and an automated assembly machine does the rest. It positions a spring over the stem to create resistance when you squeeze the lever. Then a retainer to hold both the stem and the spring in position. Now workers slip on a plastic thimble to position the rubber O-ring that goes on next. The O-ring acts as a seal between the valve and cylinder so nothing leaks out. The siphon tube runs from the valve down into the cylinder. The firefighting chemical goes up this tube, then out the nozzle. The compressed air inside the cylinder is what propels the chemical. This gauge shows if the pressure is sufficient for this to happen. After coating the gauge's threaded stem with sealant to prevent leaks, they screw it onto the valve. The valve unit is now fully assembled, tested and ready for installation on top of the cylinder. To attach it, the cylinder needs a threaded collar. With the help of a press, a worker positions it. The cylinder also needs a bottom. The technique the factory uses to permanently fuse the bottom and collar is called brazing. It's similar to soldering, but with a copper ring as a bonding metal. After positioning a brazing ring at the base of the open cylinder, they press in a steel bottom. Then they position a brazing ring over the collar. Now into a brazing furnace for 1 hour and 45 minutes at 1100 degrees Celsius. The heat melts the 2 copper rings, bonding the parts they connect. Next stop, the static paint booth, where they run a positive electrical charge to the paint particles and a negative charge to the cylinders. This draws the paint onto the surface evenly. Then it's into an oven for 45 minutes to bake the paint. Once the cylinders cool, automated machinery fills them with a fire extinguishing powder. The main ingredient is a form of ammonia. When you spray it on a fire, the heat melts the particles, fusing them into an oxygen-blocking blanket that smothers the flames. After filling, an automated machine screws a valve onto the collar of each cylinder. Now it's time to pressurize the cylinder. They squeeze the lever to open the valve, enabling a compressor to fill the cylinder with air. They keep filling until the air pressure is 13 bar, about 6 times the pressure in a car tyre. Next, they screw on the nozzle and install a locking pin. This immobilizes the lever so the extinguisher can't discharge accidentally. As the instruction sticker says, in case of fire, you just pull the pin, aim and spray. They fit a mounting bracket, and this fire extinguisher is ready for use. Although hopefully, you'll never have to. Donuts used to be called oily cakes because they were deep fried in pork fat. Nice. They were ball-shaped when Dutch pilgrims brought them to America, but then someone found that removing a nut of the dough in the center helped them cook far more evenly. And so, the donut was born. Thank goodness for that. In the world of donuts, there are two basic types, yeast donuts and cake donuts. The batter for cake donuts drops from the mixer right into boiling vegetable oil. The nozzles shape the dough as it passes. The donuts fry for about 1.5 minutes. Then a conveyor carries them out of the vat to cool. Yeast donuts require more time to make. A high-speed mixer works the yeast dough, then workers pull it off the machine into bins. From there, it goes into a hopper that extrudes the dough as a sheet. Then it's onto another conveyor belt, where a series of rollers flatten the dough sheet to just 2 centimeters thick. Next, the sheet passes under a shower of cinnamon, then hits a rotating cylinder that rolls it into a log. A small metal rod sprinkles the dough with water. This keeps it sticky, so it holds its shape while going under another flattening roller. A dusting of cornstarch keeps the dough from sticking to the blade that now cuts it into pieces. A retractable arm drops the blocks of dough 4 at a time onto a wire mesh tray. Then it's off to the proofer, a machine much like a large bread box in which heat and humidity make the yeast dough rise. This leavening process takes about 20 minutes, during which time the trays, over 300 of them, go up and down, and then out to the fryer. A gate slows them down just before the drop, so they slide in without splashing. Gas burners keep the oil at a constant temperature. Anything less and the donuts would come out partly raw. Halfway through, it's time to flip the donuts so they cook evenly throughout. After 2 minutes, the donuts leave the fryer and move through a curtain of sweet glaze. A strong air current blows off the excess, and they're done. They gradually cool as they spiral through the production area, on their way to packaging. Now let's see how they make donuts with filling. A machine separates the yeast dough into little blobs, then sends them rolling down plastic tunnels. This shapes them first into little pucks, then into rounded dough balls. Rollers flatten the balls before they enter the proofer to rise. There's cornstarch everywhere to prevent the dough from sticking to the machinery or to the conveyor belt. Row after row of donuts fry in hot oil. Then slide into a large drum that tumbles them around, covering them with a sugary coating. Now it's time for the donuts to get their fill. These nozzles inject just the right amount of jam, 2 at a time. Each worker fills 45 donuts a minute. After filling, these donuts, known as Bismarcks, are ready to go onto packaging. They're just one of the many delicious varieties that make devouring a donut a wholly wonderful experience. Sorry, I'm hungry now, I've got to go. Next, we'll be smoothing the way with shock absorbers and going back to basics with banjos. See you after the break. Welcome back to How It's Made. Shock absorbers do more than just make your ride smoother. They counteract the bounce when you hit a bump, holding your tyres to the road. Without that traction, you'd lose control. So by affecting steering, stopping and stability, shocks are a vital safety component. Wheel vibrations cause a piston inside the shock absorber to force oil through a valve. This absorbs energy, dampening the vehicle's bounce. All this happens within the shock's two tubes, the reserve tube and inside it, the pressure tube, housing the piston rod and compression valve. The factory makes both these tubes from a steel sheet sliced into strips. Inside this tube mill, coolant prevents the passing strip from overheating, as one forming roller after another gradually rounds it into a tube. Then a copper welding wheel fuses the tube closed. As the 5.5 meter long tube comes off the mill, a cutting tool chops it into shock absorber lengths. The tube making process is the same for the reserve and pressure tubes, except that the reserve tubes undergo one extra step, compressing the ends. This enables the shock to house a larger reserve tube that can hold more oil. The reserve tube's final stop is a press. A die inside stamps the part number, the manufacturing date and the brand name. Many components are made of powdered metal, mostly iron powder mixed with some graphite and copper. After a press compacts the powder in a die, a furnace fuses the particles. This powdered metal part is the valve through which the piston forces the oil. Steel discs and a spring help control the speed with which the valve operates for varying driving conditions. A stamping tool crimps the end of the tube, holding the spring in position. The valve, now fully assembled, seals the bottom of the pressure tube. Meanwhile, a press punches round steel discs into other components. These loops mount the shock absorber to the vehicle. A worker positions a cup on each one, then a robot welds them together. They insert a cup and mount unit on one end of the reserve tube, then weld it on. This unit is called the base assembly. The base assemblies now go on a conveyor, open end up, so that workers can drop a pressure tube inside each one. Automated injectors now fill it with oil that's specially designed to maintain its consistency, despite changes in temperature. Next comes the head assembly. That includes a steel piston rod and the mount on the other end of the shock absorber. Two copper welding wheels fuse the head assembly to the base assembly with a cap. This closes the unit, sealing the oil inside. Next, they weld on a dirt shield, a steel casing that prevents dirt from hindering the movement of the piston rod. Now they press a bushing into each mount. This helps absorb the vibrations coming from the vehicle. Now it's onto an automated carousel. Robots pierce a hole in each shock and inject nitrogen gas to prevent the oil inside from foaming. After injection, the robot seals the hole by welding on a tiny steel ball. Now for the finishing touch, an electrostatic paint job. A machine runs a positive electrical current through the shocks and a negative one through the paint particles. Like a magnet, the static electricity draws the paint onto the shocks in a flawless coat. In the factory's quality control lab, technicians use sophisticated equipment to evaluate how well a shock dampens movement at different speeds. The tube and valve configuration inside varies by vehicle, so the shocks on a ground-hugging sports car are quite different from those on a luxury saloon or a rugged 4x4. Shocking, but smooth. The twang of the banjo resonates in many forms of music, from country and folk to bluegrass and jazz. It's well established in the West, but the instrument actually has its roots elsewhere. African slaves are credited with bringing the instrument to the Americas, and the rest is music history. To make a banjo, they carve a lip into wood that's been steamed and bent into a circular rim. They measure the rim carefully. It must be a perfect fit for this metal tone ring, so they do a preliminary fitting. The wooden back of the banjo acts as a sound resonator. They embellish it with some plastic trim to give it a more stylish look. A chemical accelerator helps the glue dry, so the plastic trim adheres almost instantly. They sand it until the plastic is flush to the wood. This long piece of wood will become the banjo's neck. Using a table saw, they cut a long slot into the neck to allow them to install a metal adjusting rod later. The artisan widens the end of the neck with two pieces of wood to form the instrument's peg head. Next, they do some very delicate work. They embed tiny mother-of-pearl decorations into a piece of ebony. They glue that inlaid piece of ebony onto the banjo's peg head and clamp it to dry. Now it's over to a saw with 22 blades. They pass a long piece of ebony over those blades to make 22 fret slots. This is the banjo's fingerboard. Once it's been adorned with more inlaid decorations, they glue the fingerboard onto the banjo neck. At this point, they trim the edges of the neck and peg head down to size. Using this router, they give the back and sides of the banjo neck smoother contours. The rounded edges will make the instrument easier to hold and play. They finalize the shape of the neck with a rasp, then give it a thorough sanding. Here they tap metal frets into the slots on the fingerboard, then trim the overlap. Now it's time for colour. They rub stain onto the wood. When the stain dries, they spray on 12 coats of lacquer. Then polish off the job with a thorough buffing. Now all the pieces come together, beginning with the pre-fitted tone ring and wooden rim. The plastic head through which the banjo sound will radiate fits on the tone ring. They secure the head with a tension hoop and small hooks. Tightening these hooks will stretch the plastic head to adjust the tone. They attach the banjo neck with its peg head and secure it with metal rods. They screw the tuning pegs into the peg head. Then pull a string up to the tuning peg and tighten it. The wooden bridge sits on the plastic head and is only held in place by tension from the strings. Finally, they install the wooden back of the banjo. As you can see, making a banjo is a major production. No need to make a song and dance about it, mate. Now that's just showing off. So, if you have a burning desire that could do with a dousing, or you've got a sweet tooth and need to fill a hole, fear not, you can smooth the ride, because now you know how it's made. Today on How It's Made. Dress forms, a dummy's guide to bodybuilding techniques. Boat propellers, we'll bring you up to speed on how they're made. Duvets, get down. And faucets, we go to the factory where they do a plum job. But first, when it comes to dressmaking, a dummy can be a lot of help. These dummies are known as dress forms, and they're full-scale duplicates of the human body. They give the sewer a form on which to solve fitting problems. They're also used to showcase outfits in window displays, where they look pretty smart, all dressed up. For centuries, the fashion industry has relied on dummies to act as stand-ins for clients, so they don't have to endure lengthy fittings. Sometimes a form is even custom-made as the client's exact body double. To make one of these dummies, a worker soaks cardboard in water. It's strong and porous, so it can absorb a lot of water without falling apart. He positions the back half of a plaster body mould, and then he rips a soaked cardboard sheet in two. He dips his gloved hand in paste and then slathers it on the cardboard. This paste is a combination of plaster and tacky glue. He makes a series of tears along the edge of the cardboard. It's a technique called feathering. He presses the glue-coated cardboard into the shape of the body mould, building up several layers. He arranges some pieces lengthwise and others horizontally for a tight interweave. And he overlaps the feathered edges to interlock them. He taps them with a hammer to make them level, then lifts up some pieces at the centre. Now he joins the front of the body to the back. The cardboard forms fit loosely on top of one another. To connect them, he uses more paste. He manipulates the end of a paste-covered tool inside the cavity, overlapping loose layers with glue. He opens the mould to reveal the shape. This dummy is a North American size 12. That's size 10 in Europe. After After 24 hours of drying in the open air, the form goes into an oven, where it bakes for 8 hours at 177 degrees Celsius. This causes the moisture to evaporate from the form, hardening it. An employee scrapes off all the rough bits with a rasp, and then sands it smooth. Next, an employee draws lines with a pencil. He'll use these marks as guides when he cuts into the form to make the shoulders collapsible. He carves out slots on each side of the form and then peels back layers on either side of the slots. This allows him to install the hinges flush, so they won't snag any fabric. The dress form then undergoes some major surgery. He slices open both shoulders, but leaves them attached to the rest of the form by the hinges. He checks the function of the hinges, then trims along the incisions. This will allow the shoulders to be tucked into the form in a collapsing posture, a feature that will make it easy to pull a garment over it. This piece of pliable steel is a spring for a mechanism that locks the collapsed shoulders in position. He attaches it along with the rest of the locking mechanism to wooden supports in each shoulder. It's time to pull back those shoulders and show off that adjustable profile. The form is now covered in layers of linen. These pins will serve as reference points for the sewer. Another worker then washes the form with a wet sponge, shrinking the fabric to the form. Now this dress form gets the stamp of approval. A worker then gives the headless body a metal collar and caps it off with a gold-coloured finial. And now you have a body shape that's made to measure. Bit like mine, really. Oh, not in that dress. Boat propellers were invented in the early 19th century, and they've been making waves ever since. These propellers rotate in a screw-like fashion, drawing water in and pushing it out to move the boat across the water. That's why the propeller is sometimes called the screw. With a steel propeller, you can skim across the lake in a flash and a splash. To make a propeller, they start by melting wax pellets until they're the consistency of toothpaste. Nearby, a mould of a boat propeller closes, and they inject the thick wax into it. It takes about a minute for the wax to cool into the propeller shape, which will serve as a pattern for making the metal prop. Compressed air helps extract a wax funnel from its mould. It's called the pour cup. We'll see what it's for later. They wipe down the cast shapes, then soften the end of the prop on a burner and join it to the glue-coated end of the pour cup. They dip the attached pieces into hot wax to fill any gaps in the joint. A quick wash and rinse gets rid of any oily residue on the wax models. Here, a robot submerges a rack with several propellers on it in a special solution that gives them a non-stick coating. Then it's over to a tank that contains a mix of silica sand and water. The robot dips the wax propellers in it several times, then plunges them repeatedly in ceramic-based concoctions. After each dipping, the propellers go into a machine that showers them with sand. Then they dry in a room with a system of fans. The process of dipping and sandbathing builds up a hard ceramic shell around the wax. They load the propellers into a pressurized oven called an autoclave, where the wax melts away, leaving only the ceramic shells. They fire those ceramic shells in large ovens, the way potters bake ceramics to strengthen them. Nearby, molten steel is bubbling, heated to the melting point by electrical induction coils. They take a ceramic propeller shell out of the oven and pour the searing steel into it through the pour cup. The steel immediately begins to cool, causing cracks in the ceramic shell. They knock off the remaining bits of ceramic, and when they make these steel propellers, they really break the mold. Next, they cut off the molded pour cup because it's no longer needed. They grind the edges to smooth them. Then a more intensive grinding removes any corrosion on the surface. This takes skill and strength. Talk about putting your shoulder to the wheel. They lower the propellers into a series of vibrating polishers. The friction from these pulsating cones smooths out the grind lines on the propellers and adds shine. Finally, each propeller gets a once-over from a laser that measures the blades from all angles. It sends the information to a computer, which compares it to the specifications. If it checks out, the propeller will be on its way to a waterway for a big launch. Full steam ahead. Coming up after the break, we'll be getting down, down, deeper and down with duvets and tapping the trade secrets of funky faucets. Join us after the break. Welcome back to How It's Made. Down is the term for breast feathers of waterfowl, predominantly ducks and geese. Down is made up of interlocking fibres that create micro-size air pockets. These work something like a scuba diver's wetsuit. The bird's body heat warms the trapped air. The warm air then insulates the bird against the cold water. Feathers have a central stem from which the fibres emanate. Down is more lightweight and its fibres are in clusters. Bags of plumage from waterfowl farms arrive at the feather and down processing factory. The first step is to separate the down from the feathers. A vacuum hose sucks everything up into a sorting machine that has 4 air chambers side by side. In the first one, the air blows everything upward. The heaviest feathers rise just part way, while the lighter plumage floats through an opening into the next chamber. This process continues until there's only pure down in the 4th and final chamber. A vacuum hose transfers it to the cleaning machines. First, agitation and suction remove any dirt trapped inside the fibres. Then a 13-cycle hot water wash, with soap to kill bacteria and degreaser to strip the natural oils that coat the down fibres. The last rinse cycle applies an antibacterial, antifungal treatment. The next machine spins the down to remove the water. When the down comes out, it's still slightly damp. a robotic machine called the picker gathers small batches at a time and loads them into a steam dryer. After processing, the factory's lab tests a sample from each batch for cleanliness. Technicians also evaluate loft, the technical term for filling power. The higher the loft, the better the down will insulate. They measure how much space the sample fills. If the down meets specifications, the factory bags the batch for shipping to the duvet factory. A filling machine extracts a specific amount of down and transfers it to a canister. They shoot the canister's contents into a duvet's fabric shell. To keep the down evenly distributed throughout the duvet, they've sewn the shell into sections, called boxes. Emptying one tube at a time, they fill one box at a time. The down portion stays within the box. Of course, the air pressure piles it all at one end of the box, but they'll spread it out later. They close the open end of each row temporarily with a plastic clip. Once they've filled all the rows, the duvet goes off to the sewing department. Their seamstresses stitch the open ends closed and sew on labels and washing instructions. A light table allows them to see the down within each box. Then they spread it out evenly, using, of all things, badminton rackets. The fabric shell is 100% cotton that went through a high-pressure treatment to fuse its fibers so tightly that no down fibers can poke through. Besides down, they also stuff bedding with feathers. Back at the processing factory, feathers go through the same post-washing test that down undergoes. To measure cleanliness, lab technicians soak a sample from each batch in distilled water. They strain the water, mix it with sulfuric acid, and add a potassium compound. Then they analyze the color of the liquid to gauge its oxygen content. If the oxygen level's under 10, the feathers are clean enough to ship to the duvet factory. There, the feather filling process is just like the down filling process, only with bigger canisters and bigger blowing nozzles. Feathers are heavier than down and have less insulating power, but they're more affordable. Down covers only the bird's belly, and that scarcity makes it expensive. That explains why high-end bedding contains 100% down, while the rest contains either a down and feather mix or feathers alone. But there's no downside to any of those options when it comes to getting a cozy night's sleep. Sweet dreams. Faucets, or taps to you and me, were invented by the ancient Romans. But when their empire collapsed, so did their water and sewer systems. It took many centuries for plumbing to make a comeback, and for water to become available on tap. But today, they help us all lead cleaner lives. Modern taps are designed to work well under pressure, as in water pressure. They start by setting a brass spout tube on a revolving support. An automated dispenser applies silver solder to the inside rim of the spout. They press a threaded tip into the spout, then dip the other end of the tubes in flux paste, which cleans the brass and prevents tarnishing. They set the tubes against brass hubs. Then torches liquefy the solder, which flows into the joint, sealing the tube to the hub. The threaded tip is soldered in turn. A carriage now moves the spout against a buffing wheel coated with polishing compound for a mirror finish. A wheel with an abrasive surface gives that finish a brushed texture. They dip the spouts in an acid bath laced with dissolved nickel. They apply an electrical current which draws the dissolved nickel onto the brass spouts, plating them with a thin and even layer. Next, they load the spouts and other parts into a special chamber. Inside, an electron beam flashes like lightning as it spirals around a zirconium rod. This causes the zirconium to vaporize. The vapors mix with gases being pumped into the chamber and bond to the taps for a final finish that's virtually indestructible. They give other parts the same coating using the same process. Meanwhile, a blade slices a solid brass rod into smaller pieces. A variety of cutting tools machine the brass lump to make the tap's body. It will house a ball valve that controls the volume and temperature of the water. A jaw grabs the other end of the brass body to position it for more drilling. Several tools carve out holes that will act as waterways. The waste brass gets recycled. The piece of solid brass has been transformed into a pivotal piece for the tap, the valve body. With copper tubes and brass fittings now attached, they slide the tap into the base plate. That's the base plate that sits on the sink. They fasten it with screws working from underneath. Next, a robot puts one half of a stainless steel ball into a spinning vise, which properly orientates it so an automated welder can join it to the other half. The ball's openings align with hot and cold inlets in the tap body to regulate the flow of water into the spout. They insert rubber seals into those inlet holes. Rubber washers on the body will both form a seal and allow the spout to swivel. In goes the ball valve, then they cap it with a rubber seal. They screw the aerator onto the spout and tighten it with a pneumatic driver. Now they secure the spout assembly to the rest of the tap with a metal bonnet. It's time to turn the tap on. They connect it to a pressurized water source and check how it functions. Finally, they attach the handle to the rest of the tap and it's ready to ship out. They include the spray hose and support system. Those are to be installed on site. So there you have it. Taps, a real turn on. Or turn off, if you have to do the washing up, which I always do for some reason. So, if you want a fashionable, funky fitting but don't want to look like a dummy, or if you're a salty sailor and need a proper propeller, you can always get down and sleep on it, because now you know how it's made. Today on How It's Made. Bronze bells, exacting a heavy toll. Wooden aeroplane propellers. We put quite a spin on this story. Charcoal briquettes. We grilled the factory for their secrets. And gas log fireplaces. A hearth-warming tale. But first... Throughout history, Bells have played both practical and ceremonial roles. Village bells would ring to mark time and to warn of danger. Church bells would toll to summon worshippers. Bells are traditionally cast of bronze, a metal that's as durable as it is melodic. There'd be neither swing nor ring without a mould. And only a quality mould makes a quality bell. They make the mould using a pattern. This particular bell will have decorative lines on the surface, which will require a separate mould made from this 5-piece pattern. After greasing the surface with a release agent, they lower a wooden casing around it. This casing will contain a mix of fine silica sand and epoxy used to make the mould. Workers pack it tightly between the pattern and casing. The epoxy sets in 10 minutes, and they now have a sand mould with which to cast the bell's decorations. They still need a mould to cast the bell itself. They make it with this aluminium pattern. After spraying it inside and out with a releasing agent, they lower the decoration mould they just made right over it. Then on top of that, a steel casing to contain the sand mix. Workers pack the sand mix and wait for it to set. Then they flip the casing and add another section to it to contain even more sand mix. But before the next load of sand, they insert what's called the gate. This aluminium rod shapes the channel through which they'll pour the molten bronze into the mould cavity. Now they go ahead and top up the sand. Next, they form a funnel around the central channel to pour in the molten bronze. They poke the sand mix to make sure it's set, then pull out the gate. They separate the two casings, each of which contains a section of the mould. Then the patterns come out, vacating what is now the mould cavity. They tidy up the mould walls. This powdered graphite solution will act as a barrier, preventing the hot metal from eroding the epoxy that holds the sand mould together. Next, they spray on a second coat of wash. The sand is so fine that the mould would otherwise reproduce the brushstrokes on the cast bell. Now they measure the size of the pour hole and custom make a ceramic filter to glue inside. This filter will screen out the slag, oxidized particles that form when molten metal meets air. Now workers stack the two mould sections back together and clamp them tightly so that the bronze won't leak out during casting. Melting enough bronze ingots for an average-sized bell takes about 2 hours. To get a smooth enough consistency, the furnace has to heat the metal to 1,200 degrees Celsius. For a quality casting, they must pour the bronze in one continuous flow, no stops and starts. The funneling basin they made in the sand prevents overflowing. The bronze takes about half an hour to solidify and up to 24 hours to cool. Workers remove the sand mould with a jackhammer, being careful not to hit the bell inside. The extracted bell is covered in a residue of burnt epoxy. They remove it with a wire brush. Then they disengage the gate with one well-aimed strike of a sledgehammer. Now they mark the exact center point of the bell. That's where they'll install the hardware from which the bell will hang. They drill a small hole, then gradually drill it larger and larger. They can't bore a big hole in one shot because the friction-induced heat would crack the bell. They tip the bell on its side to hang the clapper, the proper term for the bronze hammer inside. Every bell this factory produces goes through 6 stages of polishing, starting with a coarse grinding belt and finishing with a fine cloth buffing wheel. 2 hours of polishing later, the bell looks as beautiful as it sounds. And that is the toll story. Ding dong. The propeller dates back to 1493, when Leonardo da Vinci sketched out the concept for a helical screw that could propel a machine vertically into the sky. The propeller is still occasionally referred to as an air screw, a term that accurately reflects its basic design and function. Wood propellers start out as a laminated block of maple wood. Lamination is a process where several layers are glued together. The block has between 36 and 48 layers, just 1.5 millimeters thick. Depending on the model, workers select a master pattern that is between 1 and 2 meters long. They lay this pattern over the maple block and mark a 1-inch center hole. And lay in a centering pin to hold the pattern in place. A worker then traces the pattern on the top of the block. He then cuts the outline with a bandsaw. This is the propeller's profile. Next, he traces a pattern on the side of the block. This is the propeller's pitch. Pitch is the amount of twist in a propeller's blades, which dictates the amount of propeller thrust. Using a pattern guide, he marks where the pitch blends into the center hub, then removes the bulk of the pitch with a bandsaw. Now he clamps it onto a computer-guided milling machine that carves the pitch to precise dimensions. The machine's carbide-tipped cutters remove 1/100th of a centimetre per pass. Precision milling just one end of the propeller can take up to 60 passes. The aerofoil is the side of the propeller that is shaped like an aeroplane wing and produces forward thrust. The pitch side and the aerofoil side. Workers use a tool called a spoke shave to further smooth the propeller. Then they verify the aerofoil's thickness and curve with a hand gauge. Next, they spray on a contrasting colour that will help them when they begin to smooth the propeller. They smooth out any remaining carving marks using a belt sander. Then they check the propeller for balance. Using a pneumatic sanding drum, they perform an overall sanding and punch in propeller specifications, diameter, pitch, flight direction symbols, and manufacturer ID. Workers hand inspect the propeller, then perform a final sanding and balance. They spray on a coat of clear enamel to seal the wood. And apply a safety colour to the propeller tips to make it visible while it's spinning. 2 final protective coats of clear enamel, 24 hours of drying time, and these propellers are ready for takeoff. Chocks away. Coming up after the break, we'll be drawing inspiration from charcoal barbecue briquettes and toasting our toes at the flick of a switch with gas log fireplaces. Join us after the break. Welcome back to How It's Made. The charcoal briquette was invented in 1897, but interest in it was slow burning until the 1920s. That's when car maker Henry Ford decided to recycle wood scraps from car making into barbecue briquettes. Ford's briquettes soon became a smoking sensation. Barbecuing with charcoal has become immensely popular since Ford's time, and every year several million tons of wood scraps are converted into high-quality charcoal briquettes. Today, charcoal briquette production starts with sawdust and wood chips from lumber mills. A truck unloads it into a pit. Bulldozers blend the material called fuel to obtain a consistent and uniform end product. As the mix travels up a conveyor, an electromagnet removes any metal contaminants. The mix falls onto a vibrating screener, which sifts out the larger pieces of wood. At this point, the fuel is still very moist. To dry it, a worm screw draws the mix up into a long rotating dryer. The dryer heats the wood mix to a searing 760 degrees Celsius. The dryer is sealed to prevent oxygen from leaking in. This allows the wood to dry without catching fire. After 4 minutes in the dryer, the moisture has been cooked out of the mix. Workers add anthracite coal to a hopper, which mixes it with the fuel. Anthracite coal is a coal that burns at high temperature. Then they mix in lime. Lime makes the briquettes turn white after they're ignited, a visual indication that they're ready to cook on. The mix, now blackened, passes under a second electromagnet to remove any metal that could damage the downstream equipment. Finally, workers blend in cornstarch, which binds the ingredients together. A worm screw supplies the mixture to a press roll. A constant spray of water keeps the mixture from sticking to it. The press rolls compact the mixture into briquettes. This happens in a fraction of a second. The briquettes contain 35% moisture and are very soft. A screener shakes out the fine material from the briquettes, which is recycled back into the process. A sweep belt transports and distributes the briquettes in a 250-foot drying tunnel. They're heated to 140 degrees Celsius for 2.5 hours. This will reduce their moisture level from 35 to just 5%. The lower the moisture level, the better the burn. A conveyor transports the briquettes to automated scales that weigh them for packaging. Each portion is the same, plus or minus 1 briquette. They release the briquettes and robots below move the bags into position to capture them. A sealing machine glue seals the bags, then prints a production date and barcode on each one. So there you have it. All that preparation and process just for you to char your chicken and burn your bangers. Who bought the beers? Anyone? Steak? That's not cooked. A gas log fireplace is a clean-burning, fully contained fireplace that's glowing in popularity. And it takes a number of skilled craftspeople to make one. It provides instant warmth at the flick of a switch. And having one will save you the task of heading out on a cold winter night to chop your logs. To make a gas log fireplace, they first screw fittings to a gas control valve. Then add the valve and gas pilot to the frame. The gas pilot is a small flame that burns continually, enabling you to ignite the gas instantly. They cap the control valve with knob extensions that allow the user to control the flame intensity from outside the fireplace. Next, they install burners and orifices. The orifice controls the gas flow in each of the burners. They attach an electrical connection from the gas pilot to the control valve. Adjust the length of the gas pilot supply line and screw the line to the control valve. Finally, they attach the line to the gas pilot. The fireplace's ignition system is complete. For safety, workers attach a device called a thermocouple to the control valve. If the flame ever goes out, the thermocouple cuts the gas supply. The unit now undergoes testing to ensure there are no leaks. What's a fireplace without logs, even if they are replicas of the real thing? This factory makes artificial logs from a mixture of fire-resistant ceramic fibres and liquid resin that binds the fibres together. Workers attach a log-forming mould to a pumping arm. Then immerse the arm in the mixture. The mixture fills the mould cavity. The mixture is soft when it comes out of the mould and is held together by the dense interwoven layers of fibres. They trim off the excess fibre and place the log on a baking rack. Then it's into an oven at 232 degrees Celsius for 5 hours. When it comes out, it's as hard as a log. Workers remove the sharp edges with a rasp. Then dip the log into a mixture of binder and heat-resistant paint. This is the base colour. Over that, they hand-paint details replicating the look of charred wood. They bake on the paint, making this decoration permanent. And it'll have no problem taking the heat. The paint can withstand up to 1,260 degrees Celsius. Back in the testing department, workers calibrate and verify the mechanism that adjusts the fireplace flame. They use a flow meter to verify the rate at which the gas flows. The back burner produces a yellow flame, while the front burner gives off a reddish glow. Combined, they look more realistic. Workers package the individual components and include some lava rock. It simulates a bed of ashes underneath the logs. adds up to a beautiful, cosy fire at the flick of a switch. Right, now, where did I put me pipe and slippers? Ah, there they are. Lovely. So, if you need reminding-a-ling, maybe this rings a bell. Or you're all in a spin without a proper propeller. Maybe you've got the neighbours round and you're charcoal briquetting it. Fear not, because now you know how it's made. Today on How It's Made. Pocket knives. Cutting-edge technology. Soapstone products. How it's made goes underground to dig up the details. Electric pole transformers. The shocking truth. And traditional snowshoes. This production process is step by step. But first, pocket knives can be used to cut rope or slice an orange. Unfold one of the blades and there won't be a dull moment. Folding knives actually date back to ancient Rome. Many centuries later, the smaller pocket-sized versions came along, allowing people to carry around knives without wrecking their pockets. They pack a lot into a pocket knife. It can contain several blades and tools, all of which can be retracted into the handle. To make pocket knives, rollers feed a strip of stainless steel through a series of dies. Like powerful cake cutters, the dies punch out blade shapes. They cut holes for installing them in the handle, stamp on the company logo, and form grooves with which a user can grip the blades. A trip into a fiery furnace hardens the metal. It's the first step in heat-treating the blades. Once they're cool, an operator places blade shapes on the magnetized rim of a rotating carousel. It moves the base of the blades under an induction heating coil. The heat anneals that end, making it pliable enough to bend and easier to fit in the pocket knife handle. A robot now transfers the shape into a computerized grinder that bevels the edge but leaves it blunt. Honing will give it a cutting edge later. Here you can see the difference the grinding makes. Vibrating ceramic pellets polish the blades with paste for 32 hours to achieve a mirror finish. A magnetic belt collects them and transfers them to the next station. Meanwhile, a rocking cutting tool carves ridges into a piece of cow shin bone. The shin bone will adorn the pocket knife handle. They submerge a bag of ridged shin bones into a vat of dye, tinting them a vibrant green. Cow shin bone is just one of many materials used to make pocket knives look attractive. Some are synthetic and others are natural. Here they're riveting a handle to the pocket knife hilt. They apply an epoxy adhesive to decorate these pieces of bone with metal inlay that's embellished with flourishes and lettering. They trim the excess bone so that it's flush to the metal liner. Next, they place a spring on the underside of the bone and brass part, followed by a rocker arm and a spacer. They finish off this sandwich with another bone-covered brass liner. They insert blades in one end, dipping each one in oil to lubricate it. A pin holds it all together. They place different blades in the other end of the pocket knife and drive a pin into that stack. A pneumatic tool flattens the ends of the pins, riveting all the parts together. Sometimes they pound a shim between the layers to open them up so the knives can move freely. It's a little fine-tuning. They grind down the pin heads to blend them to the rest of the pocket knife. They bevel the edges against a belt sander until they're sharp enough to cut. After sharpening, they retract all the blades and buff the knife until it shines. Here, a laser etches an insignia into the bone handle. They enhance the engraving with paint. And now you have a pocket knife that really makes a point. Dig deep into the history of civilization and you'll find soapstone. Over the centuries, it's been used to make everything from cookware to work surfaces to the kitchen sink. Soapstone doesn't stain or burn, and that's why today it continues to be a rock-solid choice. Production gets off to a drilling start as they bore several deep holes into a soapstone hillside. The horizontal and vertical holes form an intersecting lattice. They loop one end of a long diamond-encrusted cable and attach it to a rod. This makes it easy to maneuver as they snake the cable through one of the vertical holes. They attach a coiled snare to the cable's other end and insert it into one of the horizontal holes, jiggling it around until the snare snags the loop. Once it does, they thread the cable through the rock. They disconnect the snare and untie the loop. Then they crimp the two ends of the cable together, creating a circle over 60 meters in circumference, which now runs through the rock. They wind a section of the diamond cable around mechanical wheels. The machine moves backward as the wheels turn the cable through the rock. This action causes the diamond cable to saw through the soapstone. The process creates a lot of talc dust, the mineral that gives this stone its soapy texture. So they spray water into the cut to minimize the dusty fallout. As the cable exits the rock, it snaps back, so they make sure no one is nearby. It's taken about 20 minutes to slice through this soapstone hillside. Removing the heavy rock will require an excavator. As it pulls the soapstone away from the hillside, it breaks into chunks, each one about 2 or 3 square meters. They wash them. Then a front-end loader forks up each block and delivers it to a bandsaw. Like the cable, the saw has a diamond edge, so it easily cuts through the stone. They get several 3-centimeter thick slabs from each block, perfect for a work surface. They build apron sinks from the smaller end slabs. This type of sink was first popular a century and a half ago. But these days, computerized blades and lasers make the job of building it a whole lot easier. The laser lines serve as guides, while the blade cuts the soapstone to precise dimensions. This piece will be the bottom of the sink. They use this precision grinder to taper the sink bottom from the center out, so that liquid will flow down into a drain in the middle. They change the tooling and punch out a drain hole in the center. A constant flow of water helps keep the cutter cool and the dust down. They mix epoxy resin with hardener to prepare a high-strength waterproof adhesive. They apply it along the edge of the sink bottom, working fast so it doesn't dry. Then they press a sink wall onto the glued surface. They piece together the rest of the sink, and it's ready to blend in with the soapstone countertop. From the shower floor to the stove surround, soapstone can perform many functions with style. Coming up after the break, we'll reveal the shocking secrets of electric pole transformers and break the ice with traditional snowshoes. Join us after the break. Welcome back to How It's Made. Electric pole transformers. We see them everywhere, yet often take for granted the big part they play in our everyday lives. Their job is to transform the high voltage from electrical power lines to the lower voltage that is suitable for home use. Transformers lower power line voltage levels to ensure that your appliances don't receive too much electricity. To make a transformer, they start with two materials: paper that's coated with epoxy glue taped to a wooden block, and a 3mm thick aluminium strip, a metal that withstands the heat a high voltage current produces. They secure both materials to the block and rotate it, wrapping the insulating paper and aluminium together. An aluminium bus bar, called the low voltage lead, sends low voltage current out from the transformer. They fold the lead and move the unit to another rotating block for more wrapping. The insulating paper has epoxy glue on both sides. This glue will later melt and bond several components in place. On the next block, a worker tapes on more epoxy paper, then epoxy-coated copper wire. He rolls on a layer of wire covering the paper. Then repeats the same process, forming a second layer of copper wire. Now he solders a high-voltage lead wire to the copper wire, then rolls yet another layer of copper wire. He welds on what's called the lead wire out, the wire that'll protrude from the transformer's cylinder. and vinyl-coated wires that'll connect to different voltages out of the transformer. The component they just built is called the coil. Now using electrical steel, they build the transformer's other main component, called the core. A worker secures the coil and cores tightly together with metal strapping, which will help fix the assembly in the tank, then sends them to an oven, where they'll bake for 8 hours at 135 degrees Celsius. The heat removes any traces of humidity to improve the insulation. The epoxy glue has fused the paper, the aluminium strip, and the copper wires. The assembly fits into a steel tank. They hammer on a rubber gasket around the perimeter and bolt on an earth wire. Then they insert 3 thermoplastic bushings. They connect the low-voltage lead to the thermoplastic bushings, then bolt the bushings to the tank. They adhere an oil-filling guide to the side of the tank, then position an automated filling machine. The machine fills the tank with mineral oil, drawing a vacuum to make sure the oil disperses throughout the coil and cores. The oil is used for its thermal and insulating properties. An internal fault detector will alert maintenance crews if there's a short circuit. A lead wire is run through the thermoplastic bushing and secured in place. Next comes a high-voltage connector. The tank cover is bolted shut. The transformation, so to speak, is complete. Before transformers go into service, they have to undergo some truly electrifying tests. This equipment simulates a 145,000-volt lightning strike. Then it's into a water tank to test the transformer for leaks. If it passes, it could soon be on a pole near you. Historians believe the ancestors of North American natives brought snowshoes with them when they migrated from Central Asia some 4,000 years ago. Today, the tradition of snowshoe making lives on, thanks to skilled artisans who make them much the same way their ancestors did, with a few modern improvements. Every snowshoe frame comes from a single piece of hardwood, usually white ash. The craftsmen start with a 2-meter strip about 20 millimeters thick. Using a plane, they thin the middle down to about 12 millimeters. Then it's onto a table saw, where they taper each end to a fine point. They take the trimmed pieces, known as bows, and hammer steel braces onto each one. These support the wood where it's thinnest, so it won't break later on, during the bending process. They put the bows in a steam chamber to soften the wood. "30 minutes later, they're damp enough to bend without breaking. They start working from the middle, the area called the foe, where the wood is thinnest and easiest to bend. They wrap it around a steel form on a bending jig. Then lay one tapered end over the other and tack them together. Now back to the steamer for a second bow to complete the pair. A temporary crossbar over the width of the frame holds the shape. They use different steel forms to shape different snowshoe models. They set the frame on a bending machine, called a press brake, then position a wooden bar on the frame to act as a fulcrum. As the press comes down, it curves the tip of the frame about 7 centimeters upward. They insert a crossbar lengthwise to hold the bend in place. The frames are still damp from the steam chamber, so they need to dry out for several days. Only then can the temporary crossbars safely come out. The craftsmen then sand the wood to a smooth finish. They drill slots on the inside for the 2 permanent crossbars, while another machine stamps those bars with the company logo. It takes just a quick stretch to insert the bars, one near the toe, the other near the heel. Now the frames go for a dip in a vat of oil-based varnish to seal and waterproof the wood. Once the varnish dries, the frames are ready for lacing. In keeping with tradition, the laces are animal hide. Wetting it makes it easier to cut into long, thin strips. A skilled weaver threads her needle, then begins by hooking the raw hide lace through a nylon thread that runs along the inside perimeter. She nimbly builds up a pattern of webbing that always begins and ends with a series of triangular shapes. This intricate weaving technique is a traditional skill, passed down through generations of First Nations women. She finishes by wrapping up the heel end of the frame with raw hide, then pulling it tight. Now that the toe piece is finished, she starts weaving the middle piece. Using a larger width of rawhide, she builds up another web of triangles, this time knotting the strips directly onto the frame. Finally, she weaves an opening to leave room for the bindings that hold the snowshoe to your boot. Once the rawhide dries, the webbing will lie taut across the frame. The last step, another coat of varnish to seal and protect both the wood and webbing. And now these traditional snowshoes are ready to make some cool tracks. So, if you ever need to make a portable point, or you've got into a lather over your soapstone products, you'll make sparks fly with electric pole transformers. 'Cause now you know how it's made. Today on How It's Made. Steel shipping drums. They have the competition over a barrel. Police whistles. A device that's a real traffic stopper. Miniature train cars. Historic designs with a great track record. And glass blocks. This report's perfectly clear. But first, the steel shipping drum was invented in the late 19th century for the oil industry, which needed an alternative to leaky wooden barrels. But those first steel drums also leaked from their soldered seams. Welding them proved to be the solution, giving this container an airtight reputation. It's a product that really delivers the goods. To make steel shipping drums, a punch press cuts and forms the bottoms in one swoop. A conveyor shuttles the bottoms down the line to a turntable. As it rotates on the turntable, a nozzle sprays sealant onto it, coating it completely. They stack up the drum bottoms. Meanwhile, Another punch press shapes steel discs into tops for the drums. Rollers turn up the outer edge to a precise measurement. Next, steel fittings tumble down a vibrating conveyor to a machine that simultaneously punches threaded openings in the tops and inserts the fittings. One hole is for opening and closing the drum, while the other is to vent. At this station, they check the thickness of the sheet steel that will be used for the body of the drum. The thickness varies depending on what the container is to hold. A machine called a shear slices the coiled steel into sheets. The steel sheets then move onto a forming machine, where rollers curl them into a tubular shape that's the drum shell. Automated pushers then move each shell through an electric resistance welder. It generates heat to weld the side seam, bonding it from both the inside and the outside so it won't leak. The shells roll down to a machine called a flanger. The flanger stretches and presses the outer rims at both ends, creating a lip. Then it's over to a machine called a beader. Its rollers bear down on the shells to make grooves called rolling hoops. These rolling hoops add rigidity to the shells. The shells now travel down another conveyor and merge with the drum tops. Automated pushers deliver a top to the base of a shell. The shell rotates in a spinning clamp as rollers curl the edges of the top and shell together. This creates an interlocked seam called a chime. Another roller then flattens the chime. Mechanized arms flip the shells so the bottoms can now be installed. To join the bottoms to the shells, rollers form another chime. These interlocking seams are comprised of 7 layers of steel, making them leak-proof. That's critical, since the steel drums may be used to transport hazardous goods. The drums now move forward to a testing station. Here they inject air into each drum and check the seams for leaks. The seams have been soaked, so if bubbles materialize, it signifies a problem. The steel drums then go for a whirl under a paint gun. It sprays them with enamel paint as they rotate, giving them a protective sheen. Black is the most common colour for these shipping containers, but custom colours are sometimes ordered. The steel drums then journey through an oven to bake the paint to a hard finish. Then they gauge the thickness of the paint with a special tool to confirm that it's thick enough to withstand rusting. They plug both openings and put a temporary seal on the vent to prevent tampering. After that, these steel shipping drums are ready for the long haul. It was in the late 19th century that London police started using a special whistle to get attention. It was lightweight and had a piercing sound, and was a real improvement on the hand rattles they'd been using. That same design is still used today. It's why a police whistle is a real blast from the past. Blowing the whistle on lawbreakers and traffic offenders is an ear-splitting ritual. The average traffic officer blows on one thousands of times a day, so the whistles have to resist a lot of spit. The whistle's body is made of high-grade brass tubing, in which they punch 2 slots. These are the sound holes that will allow the noise to escape. Using hydraulic pressure, they stamp the brand name onto the tube. Next, they make the mouthpiece. Rollers sculpt a piece of spinning brass into a shape that's a bit like an hourglass. With the mouthpiece complete, they use a hydraulic punch to bend a piece of brass into a part called the slab. The slab will be used to create two sound chambers inside the whistle. They fit a loop onto an end cap. The loop will make the whistle easier to hang onto. A rotating press bends the loop's tab against the inside of the cap to fasten them together permanently. Next, they attach an end cap to the slab and then force the slab into the cavity of the whistle, splitting it into two chambers. A police whistle actually produces two notes at once, giving it that distinctive timbre. These two separate sound chambers will produce two different pitches. They now dip the ends of the whistle in solder paste, and then hammer the looped cap and mouthpiece onto the pasted ends. The solder paste is a special lead-free compound, so the whistleblower won't be exposed to toxins. They also insert solder wires in the whistle chambers before capping the ends. These solder wires will act in conjunction with the solder paste to seal the whistle, in a process that happens next. The whistles move through an electromagnetic induction coil, which heats them to 220 degrees Celsius. This causes the solder paste and wires inside to melt and flow into the whistle's seams. Then they quench each whistle in an acid bath, which hardens the solder, sealing the whistle seams. Next, they lower the whistles into a nickel bath, where positively charged nickel ions migrate to the negatively charged whistles. Now, it's time to make a noise. They test each whistle with compressed air. The tiniest pinhole will cause a whistle to fail, and that happens in 3% of them. Failure is a crushing experience. They flatten the rejects and send them to a company that will reclaim the metal. On both land and sea, whistles are the sound of authority. Here they assemble a bosun's pipe used by naval officers to issue commands and salute dignitaries. There's a tiny hole in the ball at the end of this pipe. The player opens and closes that hole with his hand to change the whistle's pitch. And with that, production comes to a screeching stop at the whistle factory. Coming up after the break, we'll take a scaled-down journey through the world of miniature train cars and get a clear picture on the manufacture of glass blocks. Join us after the break. Welcome back to How It's Made. Making miniature train cars is all about the details. Every feature is scaled down to a fraction of the size of the real thing. And nothing is too small to replicate. But remember, this is more than just a toy, kids. This is a collectible. On a miniature train track, The past comes full circle, with replicas of trains from days gone by. They start with historical photos and drawings of actual train cars and scale them down to 1/48 size. They feed polystyrene pellets like these to an injection moulding machine. It melts the pellets into a thick paste. The 4 sections of a mould close, and nozzles pump the plastic into it. It oozes into all the grooves and hardens almost instantly into the shape of a train car. Then they clip off the excess plastic. Here's a view of how the 4 parts of the mould come together to shape melted plastic into a boxcar. They even make holes in the boxcar to attach accessories. And they impress details like ridging that mimic the steel ribs of the original life-sized wagon. Using other moulds, they replicate doors, rails, brake wheels, and other accessories. The assembler clips the parts off the framework and files down the rough sections. That's the brake wheel she's snapping onto the end of the model. Using a knife, she trims excess plastic from the wagon step. Then she glues a weight to the bottom. Making something to scale is a bit of a balancing act. Finally, she attaches air brake tanks to the underframe of the wagon. And it's time to spray paint the model vivid orange. It's a colour that would have been used on an actual boxcar, combined with white. For that two-toned look, they hold the model in a paint shield to protect the sections that are to remain orange, as they spray the sides white. This technique ensures the paint job has clean lines. They leave the wagon to dry overnight. Other wagons receive a less flashy paint job. This one is basic black, and it's the perfect canvas for white lettering. A pad picks up the ink from letter engravings on a printed plate and transfers the image to the wagon. Metal wheels now roll off a revolving conveyor. They funnel into mechanisms that press fit them onto each end of the metal axles. The wheel and axle assemblies drop into a bin below. 2 sets of wheels are now installed on a plastic framework. They attach the framework to a coupler, the device that links the wagons. They screw the 4 wheels and coupler assembly onto one end of the car, and they install another one on the other end. They snap the couplers together to connect the 2 model wagons. In the world of model trains, a little grime is just fine. They make it look dusty on purpose by misting the model with paint. The painter layers colours to get just the right effect. This technique adds an element of realism to the model train. It's all a matter of preference. Some hobbyists prefer this weathered look, while others like their models shiny and new. The model trains have now rolled off the assembly line, and they're ready to roll down a mini rail line. It'll be a whistle-stop tour, but don't worry, it'll come round again in a couple of minutes. When it comes to building materials, glass blocks are clearly a classic. In the 1920s and 30s, they were a cornerstone of the Art Deco style of architecture. Today, glass blocks are still popular for creating walls, windows, and stunning design features. A stylish way to maintain privacy and keep the light. glass blocks aren't just decorative. They insulate from heat, cold, and noise. They begin with just 4 ingredients: recycled glass pieces called coloured, sand, soda ash, and limestone. A computerized system portions out each one and feeds them into a melter. This giant furnace heats the batch of ingredients to a fiery 1,500 degrees Celsius, transforming them into molten glass. The melter pumps out enough molten glass to make 1 half block at a time. Automated shears slice it off. The gob of glass then slides into a waiting mould. A plunger pushes the gob down, spreading glass throughout the mould cavity. Its waffled surface imprints that pattern onto the glass. Pipes overhead blast ambient air that cools down the molten glass drastically, from 1,000 to 600 degrees Celsius in just a few seconds. This way they don't lose their shape when this retractable arm extracts them from the mould and lays them on a conveyor belt leading into a sealing machine. This is where 2 half blocks join together to form a full block. Entering the machine, each piece passes over a series of burners that keep the glass temperature constant. Sudden cooling could crack or shatter the glass. The machine then slowly reheats the half blocks until their edges start melting. They enter the part of the machine called the squeeze station. There, an automated press forces a top and bottom half together. Their melted edges fuse, forming a single block. The blocks now travel into a leer, an oven that cools the glass at regulated temperatures over several hours. This annealing process prevents cracking and allows the glass time to set properly. The glass temperature going in is about 1,000 degrees Celsius. Coming out, it's down to 80 degrees. The blocks are now ready for inspection. Workers use digital alignment gauges to make sure both halves are flush. Then they run a straight piece of steel along the block's surface to check for any distortion. Each and every block must meet precise standards for both size and shape. This finished block is a 19 centimeter square and 10 centimeters thick. Building with glass blocks is similar to building with bricks. You use mortar to stick them together. To prepare the blocks for mortaring, workers now place each one into a separate station. As it spins, nozzles spray the edges with liquid vinyl. This coating will help the mortar stick to the glass surface. One last step. An inkjet printer applies the product code, along with the manufacturing date and time. The quality control department runs samples through an impact test. A worker drops a weight through a tube onto the side of the block. This verifies the strength of the side wall and the seal between the two halves. Finally, the glass blocks are ready for shipping. Workers pack them into cardboard boxes that have block-sized sections to keep them safe during transport. Glass blocks come in so many shapes, sizes and patterns that the design possibilities are endless. Both practical and beautiful, they're clearly a construction classic. So, next time you want to roll out the barrel and drum up some support, or create a blast from the past and blow your own whistle, don't worry, because you'll always be on the right tracks, even if they are miniature, because now you know how it's made. Today on How It's Made. Ice cream cones. We have the scoop on how they make them. Tent trailers. This story is about to unfold. Shoe polish. All the shine and plenty of substance. And pliers. A truly gripping story. But first... The ice cream cone is the original edible container. Invented over a century ago, it adds crunch to the melt-in-your-mouth taste of ice cream. And it's one container that doesn't end up in the waste bin. So you could say it adds a bit of virtue to the guilty pleasure of a double scoop. The first ice cream cones were rolled waffles, and today's cones are simply modern versions of that. To make a waffle cone, they start with a lot of dark brown sugar. They add caramel colouring, along with some secret flavouring ingredients. They pipe water into the blender. It's ice cold to keep the batter from getting too sticky. A computer controls the flow of flour into the mix from a tank a floor above. They add vegetable oil as a giant beater mixes all the ingredients. The batter then flows out of the blender and into a refrigerated tank. At this point, the blend is the consistency of pancake batter, and an agitating blade keeps it that way. Next, nozzles deposit measured amounts of batter on a baking plate that looks like a moving waffle iron. Top plates flip down and the baking plates roll through a gas-heated oven for a quick bake. The top plates lift up, revealing the cooked waffle patties. Automated arms transfer the patties to rolling tools. The tools grab them and twist them into cones. The cones fall down a chute and ride an open elevator up and down to cool and harden. The waffle cones slide down another chute and move into lanes on a conveyor. Automated fingers adjust their position to prepare them to slide into paper jackets. A computer with a camera counts the cones and sends a message to a machine that stacks them in the right increments. Here, a technician activates a device that pushes on a ball inside a cone to test the cone's breaking point, proving that this waffle cone can survive some serious snacking. Over in the sugar cone department, the baking plate system is designed differently. It makes patties that are fan-shaped and have a flat edge. This, combined with the type of batter used, means sugar cones are stronger than waffle cones, so they're a more popular choice for hard ice cream. Packers stack the cones in styrofoam trays. Then the packages travel through a curtain of high-density polyethylene film. A heated sealer finishes the wrapping job. An X-ray machine sends information about the contents to a computer that counts the cones and alerts the company to any problems. Next, automated arms pick up cartons and open them, so the packs of cones can be inserted. Meanwhile, they mix up colourful batches of cake cone batter. Cake cones are less sugary and have more cake-like texture, as the name implies. They pump the batter into upright moulds. Cake cones are shaped very differently than waffle and sugar cones. They have flat rather than pointed bottoms. Metal cores plunge into the moulds to complete the shape. This action also affects the texture of the cake cone, so it turns out flakier. They pass by a gauntlet of gas heaters to bake them. The cake cones then fall down a chute and head towards the packaging station. Unlike the other cones, they don't need a long cooling down period. They come out flaky and crisp. mechanical arm picks up paper sleeves and drops them in front of the cones. It's all perfectly timed. These cones in all their various shapes and sizes are on their way to an ice cream van near you. And if it's anywhere near me, I'll have a 99 with hundreds and thousands. And the nuts. Oh, go on, just the 99. Tent trailers allow you to travel without reservations. Who needs a hotel if you can park the pop-up? Besides, you don't get fresh air and campfires at a hotel. Tent trailers have been around since the early part of the 20th century, and you could describe them as an overnight success. In a tent trailer, you can camp with modern conveniences, and that should make you a happy camper. To make one, they weld tubular steel components together. This establishes a solid framework for the tent trailer. Once it's painted, plumbed and partially wired, they add wheels, bolting them into place. The water tank goes in next. Then they string aircraft-grade steel cables from corner posts to a central bar. This bar is called a whiffle tree. Cranking up the whiffle tree will cause the cables to lift the corner posts, raising the trailer's roof. They wheel the trailer to the next station, where they lower the vinyl-covered wooden floor onto the chassis and secure it with screws. Then they connect a cluster of wires to the wires already installed on the chassis to run things like kitchen appliances and stereos. They rivet the interior front wall to the steel bulkheads and the trailer chassis. Then they thread the wiring through the bulkheads to the trailer's side lights, and then install the exterior panel. They slide the roadside panel over the lift posts and secure it. The curbside exterior panels come in two pieces to create a space for the trailer door. Corner moulding completes this assembly. They move inside and install the framework for bench seating. They install the lower cabinet for the kitchenette, and then join it to the upper cabinet with a long metal hinge for easy pivoting. They insert the mini fridge, and this folding kitchenette is done. This is the pull-out platform for one of the mattresses. They slide it into channels in the exterior walls. But there's more work to do before anyone can take a nap. They stitch together pieces of water-resistant fabric to make the tent for the trailer. They sew 5 sections separately, then zip them together at an inspection station. They scrutinize every seam for flaws. None will be tolerated. Once the tent passes inspection, they fit it on the trailer, one section at a time. Then the trailer is ready for the roof. To build the roof, they sandwich many materials together, and that takes a lot of industrial adhesive. They roll it onto these plywood slats. And these foam insulation boards also get a generous coating. They place the glued foam onto the roof's fiberglass outer skin. They position the wooden slats along the perimeter and add bands of metal for more reinforcement. The final layers are vinyl-coated plywood. It will be the ceiling of the trailer. A large roller compresses the glued layers together. After grooves and notches have been cut into the roof, they wire it and install 12-volt interior lights in the ceiling. They add trim to the roof's edges, along with a gasket to keep it watertight. They fold the roof's flaps in a tray-like configuration and cap the corners. They're now ready to raise the roof and install the tent. They insert it into grooves in the trailer ceiling using a pneumatic hammer. This tent trailer is now ready to pop up anywhere. It can accommodate a small family and is equipped to feed them outdoors or inside. It even comes with a screen door, because who knows when adventure will come knocking. Coming up after the break, shoe polish, a shining success. And the gripping story behind pliers. Join us after the break. Welcome back to How It's Made. Mud and scuffing have long been the ruin of shoes and boots. In medieval times, they used wax to soften and waterproof leather footwear, but it didn't polish it. By the early 20th century, shoe polish as we know it was invented. It gives shoes a shine and makes them last a long time. A great shoe shine takes a bit of polish and some elbow grease. A vigorous brushing can enhance the job and help transform your shoes from drab to fab. To make shoe polish, they start with mineral spirit solvent and different combinations of carnauba wax. They load the waxes into a wax melter and heat them to 127 degrees Celsius. They cook for 15 minutes, while beaters blend it all together. This is dye fluid. This one is a deep black shade. In another tank, they add dye fluid and waxes to the solvent blend. Agitators mix it for 3 minutes. Tin container bottoms tumble down a chute and up a magnetic conveyor belt. A worker flips the tins right side up, then pushes them onto another conveyor. It lines them up and they're ready to be filled. Automated arms space the tins as they arrive at the filling head, so they don't bunch up. The filling heads inject hot liquid shoe polish into the tins. The nozzles fill the tins with a precise amount, so there's no overspill. The polish now needs to cool down and solidify, so the tins travel through a cooling tunnel. When they emerge, the polish is a thick paste. Workers perform a breaking strength test to be sure the final product has the right consistency. The polish-filled tins now funnel onto a conveyor that merges with a feeder loaded with lids. The feeder lowers the lids onto the tins full of shoe polish. A compression wheel presses the lids in place with just the right amount of force. And this polish is now ready to shine. There's a different packaging system for liquid shoe polish. A blow molding machine forces hot air into plastic to form containers. Then the mechanized rack holding the containers rotates and places the newly formed bottles onto another conveyor. It moves them under a flame which melts the rough edges. Revolving conveyors move under filling heads which pump liquid polish into them. Workers insert valves into applicators. Then this machine press fits the applicators onto the polish-filled containers. Using hydraulic pressure, another machine snaps clear domes onto the applicators. Rollers affix labels onto both sides of the bottles. The bottles then move through an inspection station. A mirror helps workers scrutinize the labeling job. A technician takes a reading of the gloss on some leather. He applies some paste polish and rubs it in with a horsehair brush. He takes another reading, and the gloss on this leather has increased by a factor of 2, which means this polish passes muster and it's ready to add luster to your footwear. Okay, own up, who's got yellow shoes? Pliers date back to around 2000 BC. Ancient drawings show Greek gods using pliers at the forge. Today, forgers still make pliers, but they use automated tools to shape the metal. Pliers are standard equipment in the tool belts of electricians, plumbers, and mechanics. Pliers have 3 basic parts: handles, a rivet, and jaws. All the parts start out as a steel rod that metal workers forge into shape. First, a powerful electric furnace heats the steel red hot in just a few seconds. Then a metalworker sets one sizzling rod at a time on a forming die. A massive die forger hammers the rod against the die with tons of force. It takes up to 4 strikes on separate impressions for the rod to acquire the die shape. Then the forging is placed into a press that trims off any excess steel. It takes 2 forged rods to make 1 pair of pliers. This pair will be for gripping, so the next step is to machine the teeth into the jaws. Workers set the plier halves into the broaching machine. Its tiny cutters, dozens of them, shave away steel under a shower of lubricant. When the cutters pull away, each half now has a nice set of teeth. They heat treat the steel to harden it, a process called stempering. The plier halves travel through a gas-fired furnace for about 2 hours, at a temperature in excess of 800 degrees Celsius. Then they quench the steel in salt water to cool it rapidly and evenly. The teeth on these pliers will have to take a lot of abuse, so they get a laser heat treatment to make them even harder and more durable. Now the pliers are ready for assembly. For gripping pliers, a worker inserts a single-piece rivet and joins the 2 halves. He then sets the joint into a machine that spins at high speed, generating force and friction to set the rivet. Cutting pliers are also held together with a rivet, but the setting process is different. The parts go into a press that applies both heat and pressure to secure the rivet firmly. Next, workers insert the cutting pliers between 2 stone grinding wheels. Again, lubricant prevents the steel from overheating, as the wheels wear down the rivet until it lies flush with the plier surface. Next, the cutting pliers go into a gas oven for another 2 hours of heat treating, a process called tempering. When they come out, they cool in an oil solution, rather than the salt solution that cools the gripping pliers. Steel is a finicky material, so it's critical to manage the heat treating process meticulously, otherwise the metal will be substandard. After heat treating, the pliers go for a bath in a vat of rust inhibitor, that helps protect the steel from corrosion and lubricates the riveted joints. A robotic arm runs one pair of pliers at a time against a grinding belt, polishing all surfaces except the handles for a sleek finish. Then a laser engraves the company logo and product number. Automated bars now lower hundreds of pliers handle deep into a tank containing liquid vinyl. No messy drips, as before dipping, the factory heats the pliers to help this coating stick to the steel. From there, the pliers go straight to an oven. The heat hardens the protective coating, cushioning the handles so they're easier on the hands. Whatever their shape or size, pliers are a toolbox essential for anyone looking to ply their trade. So, if you need to get your fingers round a frozen fancy, or you're crazy for compact camping, you can set a shining example, because now you know how it's made.